Mhm. Yeah, I mean, maybe, but why not? Why not try? I mean, I'm not trying to fit I'm not trying to fit a dispersion relation or anything like that, but we're just looking at the ratios of fields. Yeah. Yes.
Right, let's thank Shadi again. And the next talk is by Sergio about phase space transform.
Thank you. Thank you for giving me the possibility to have this talk. It's an excellent conference. I like it since forever. So this has been a work that we published recently. In the past 2 years, there's a sequence of work, actually, mainly with Domenico Trotta, and it's about the interaction between turbulence and a shock. Here, there is only a partial part of the co-authors. The family is much bigger, especially now that there is a lot of other groups working on this since then, since this first paper appeared. So the concept is easy. So shocks are usually observed in the heliosphere and in astrophysics. I'm not gonna try to convince you about this, or as well as turbulence is ubiquitous. So there are these two main aspects, shocks and turbulence. And imagine a large shock starts SAMA, CME, will encounter turbulence. So it is really natural to think about an experiment, a thought experiment, maybe, which is the interaction, how the particles are accelerated while the shocks propagates against a turbulent medium. And so it's a very simple cartoon, and it has been a cartoon for years. So I have to say that it was very inspiring, the picture by Gary Zank, where he's envisioning like this shock going against a sequence of islands. Actually, there are many more papers on this sketch of a shock going against islands and particles that gets a lot of kicks, both from the shock and from the island locally. So it is very intriguing, and probably is an ubiquitous setting, right? Because the shock is going to always encounter some even tiny small amount of turbulence, no matter how big will be. So this is already gives us some ingredients. We must study this problem, probably varying also the level of turbulence, right? To have a broad understanding of this. There have been some suggestions about shocks and turbulence, more than turbulence, shocks and randomness. So there were some numerical experiments where they were sending a shock through some very small-scale random fluctuations. But what we are going to do now is try to transform this picture into reality, I mean, numerical reality. Okay. So that's really a method. So we imagine this wind, which is like sending some turbulence against our planet. Then there is the bow shock, there is an obstacle. And then, therefore, I send structures and waves, and both of them against this shock. And actually it's a very interesting process, especially for the solar wind, because in the solar wind you have a certain beta, and you have some structures with a correlation length. And this will be pretty much, for example, in the MHD range for the energy containing scales. But at some point they will encounter this shock, and the width of this shock, it has kinetic physics. So that's what we did. We prepare a simulation of turbulence on one side, and on the other side we prepare a simulation of a collisionless shock, and then we squash them. Huh? Okay. Yes, this is the first part. This is a compressible pseudospectral simulation with high resolution. We prepare this because we want to create naturally the vortices, current sheath, this sea of islands and reconnection locally in the MHD frame. So then you need to filter it, right? Because now we break the typical periodicity of our boundary condition, because we want to send the turbulence, this blast of turbulence against the shock. Therefore, you need to wind of the potentials and send from left to right turbulence and from right to left the shock. So this is a first try in vacuum. There are hundreds of paper with this kind of shocks that they move with a collisionless code. Of course, while they move, they accelerate particles. Particles get kicks, they form like a beam, and is all really well known. And sometimes particles interact with the shock, break the shock front a little bit. So you can observe some randomness and some level of turbulence here, but this is a trial with vacuum, no turbulence, and the mean field is oblique to this shock. So what we did, then we prepared this sequence of simulations by varying, we want to give a recipe, we are varying the level of turbulence. In one case it's like 40% turbulence, the second one there up right is 80%, so solar wind will be in between the first and the second. Then it was like 210%, why not? Because you can have a mean field which is like weak, in I don't know, at the heliopause, or somewhere else. We provide a variety of this and see how it varies. But what is interesting is that the distribution of particles is the black one without turbulence. It has two peaks. Is the bulk of the motion, is the thermal particles and the beam, and they are very clear. When you introduce turbulence, you spread these two peaks, and they really like diffuse in this velocity space. You accelerate particles, but you also decelerate particles, because turbulence can trap particles, okay? Now, usually we always speak about acceleration, but really, sometimes the plasma can be decelerated, right? Why not? So, really, turbulence is spreading these two populations. And really, now, I want you to think on the other side of the phase space, in the velocity space. So imagine a particle in the velocity space. You always think of particles in the physical space, but now forget that and think to the velocity space. A particle is an element that follows the trajectory, right, in this following the Vlasov equations. So it's doing some erratic motion also in the velocity space. So for the case with zero turbulence, if you take a particle into the beam, it will stay there. Okay, particles are, you produce a beam, a nice beam, and will be coherent forever, pretty much. If you add the turbulence, then particles can escape these boundaries. Because somehow you are breaking this closed surface, and then the particle can just scratch all over this volume and go from one population to another. This is for a single particle. Then this kind of distributions, it's averaged all over the upstream region, in front of the shock. Yes, yes. No, they spread. They spread also to higher energy. Everything. No, but this is the beam, and this is the bulk. Okay. Yes, it is low. Then it's a matter of. Absolutely, yes. I can see this effect. Yes. More diffusion. So you have a spreading of particles in the space, and you have a spread of particles in the velocity space. You have diffusion in this phase space. That's what it is. So if you have a diffusion, usually a good technique, for example, usually is done in hydrodynamics or MHD, also with Vlasov moments by the group by Bill, for example, you can coarse grain your equations and understand how this mixing is happening, yeah, with that coarse-graining technique. So really, now you have to decide like the strategy. This is a very particular problem where you have a beam and a bulk and you have turbulence. So we discretize like the space, like with squares, of sides in the inertial range. Then we show that these results are self-consistent in the inertial range, which is good, actually. So we can apply this probably to spacecraft analysis. And then you discretize the velocity space into shells, okay? Shells of radius W, where you will have like a blue region, which is like the thermal particles, and everything that is out of this blue region is the suprathermal particles, okay? Then you can integrate in both space and velocity space. Okay, you can do this. It's actually is not that difficult to do it. Just take Vlasov. Vlasov is already a coarse graining of the particles. So you take Vlasov equation. You can use a kernel, a filter. The filter is something like I don't know, a Gaussian, or it can be a boxcar in this case. And you can filter the Vlasov equation and obtain a reduced moment. This n of L and W is the number of particles in a square of side L until a cutoff W in energy. It's very similar to the Parker idea of reduced moments. So you see, it's a partial moment from the VDF, and it's quite good from the experimental point of view because it's an integral. Experimentalists will love this because you don't need a lot of details. You are averaging in space and you are truncating in the velocity space. So you are really reducing the uncertainness about the details. So with this coarse graining, you obtain a density continuity equation where you have a divergence of a flux, like a continuity equation. Then you have a term which survives there because your velocity distribution function is not a Maxwellian at a shock. Okay? Most of the models assume like double B Maxwellians or bi-Maxwellian. This is a complex distribution function. We know it. There are beams, there are multiple beams. People that are familiar with the magnetosheath analysis, they know that the velocity distribution function is very complicated. So this term survives, it's like a transport in the velocity space. And then there is the rest of this coarse graining, something which is small scales, that we leave it to the small for now. But now the meaning is very immediate. I have this core and the beam, and there will be regions where this acceleration will find a bridge from the core to the beam, or vice versa, depending on the electric field. Okay? So I have two communities, the red one and the blue one, that will communicate, depending on the stochastic electric field. Okay? So you can measure it, and what you can do at the end is doing like a paint, a mosaic, a very simple one. You can identify regions where you have spread in space of particles or contraction, or you can identify a region where you have like acceleration or deceleration of particles. And this is the middle one. You see there are patterns of acceleration and patterns of deceleration where the beam population goes back into the thermal population. This is really at the limit. Only turbulence can do that. Indeed, if you do this experiment without turbulence, you observe a delta in this distribution. It means you don't have any access, any communication between these two sectors. Well, turbulence opens this, if you... Sorry? The sky. Okay. By just separating the two populations, we can span it. It's self-similar. Yeah, but it's self-similar. This is an excellent point, of course, because you can scan it. Mm-hmm. No, it's going to be a small-scale residual, as in the Germano techniques for hydrodynamics. When you coarse grain, you have like... Yes, it's diffusing inside the grid. Something lost. Yes, something lost inside the population and inside the coarse graining. Okay, something which is lost from... Exactly. Here we go. So what we observed is that turbulence is that the diffusion is enhanced in front of the shock, but also we observed that some of the structures were passing through the shock. Actually, energetic particles were going through, accelerated even in the downstream. So at this point, we analyzed some data. So we can use simulation to guide us and understand more the data. We took two data sets, one AU from wind and the other one with MMS. They are somehow connected, but I'm not going to argue about that. It's not going to be the same parcel of plasma, right? I'm not so crazy, although a little bit. But you know, it's going to be two pieces of plasma that are statistically like similarly almost connected. Okay, except one is solar wind, the other one is the shocked wind. So first, we are going we would want to just understand how much of these coherent structures are going through the shock. So what we did is first you can measure, like yesterday we saw excellent reviews on this. You can measure like the burstness of the magnetic field by this parameter here, which is called PVI, and is like the gradients of the magnetic field, and it somehow it's measuring like the burstiness, the reconnection regions probably, candidates for reconnections. And the signal is very similar in both cases. Solar wind, the magnetosheath, they can vary a little bit the amplitude, but they are both intermittent. You will have like reconnection in both cases. What is varying is this other parameter. We, with Francesco Pecora, we kind of like built a tool which is able to measure the local magnetic helicity of a signal. So how much the plasma is helical in a point. It's like sort of like a running magnetic helicity. So here in the solar wind it's pretty low, while there is a strong enhancement of this helicity in the magnetosheath. There is such a large big literature on this. This is very well proven, but now we will see why this is interesting. It's interesting because now we have the simulation and we can understand this. We are sending blobs of turbulence, coherent structures, this shock constantly. And in the upper region here, there's this nice and smooth coherent structure which is going against the shock, which is coming from right to left. When it passes the shock, you see immediately, especially in this part here, there, right, is growing magnetic helicity. Although it's becoming even more noisy. So it's destroying the current, but it's enlarging the magnetic helicity, which is large scale. Magnetic helicity is a quantity which is like really large scale, is measuring you the coherency of the magnetic field. So we observe that the shock is pumping magnetic helicity, and also the anisotropy is produced. I admit, still, I don't understand the phenomenology of like the increase in anisotropy. Maybe one of you can. And well, we have limitations, right? I do. Here we go. Is one. You won so far. Yeah, thinking about maybe you have a solution. I don't. I have probably a qualitative solution for why the magnetic helicity is growing at the shock. Is because if you take the MHD equation and you write the density of magnetic helicity in one point, you see it has this advective term. This is negligible. It has a piece with divergence of u, and while the shock passes, it's pumping the helicity. It's very basic. So basic that maybe nobody saw it so far, but it's okay. It's okay. So here, these are the conclusions. These are two of these works. Some other groups, like the Gerritsen, is actively working a lot on this, and it's very exciting because we find complementary, most of the time similar things. So, and this has been chosen, not this one, but this as the cover page of PNAS. So, some months ago, probably a year ago. So, thank you.
Thank you very much, Sergio. Any more questions? There,
How the correlation lengths change across the shock, because if you are generating electricity or these flux source, the correlation length should decrease in the microchip.
No, it's decreasing. The correlation length of energy is decreasing. Careful, because helicity and magnetic energy are two different invariants. Okay, and magnetic helicity usually is larger scale. There is a paper by Goldstein and Matthews where they try to measure this correlation length of the helicity. Is usually larger, right? Maybe Bill can say more about that. So, but it is true that you are destroying the structures and it reduces. So it's very similar. Although I would like to have a larger box to see more, so then I need more computing times, more money, give me money. And
more questions for Sergio? Yeah?
So if you don't have electricity to begin with, if you have zero electricity after, then you don't generate new electricity?
you do it. That's why we do. This is fundamental, because we do our MHD simulation exactly because of this question. We do the MHD simulation starting from zero helicity. It produces immediately, because of the relaxation processes that Pecora was describing. It produces, then we can have a coherent field to squash against turbulence. That's what we did all of this.
You don't need a seed.
No, we don't need it at the beginning. It will produce immediately this. Even cross-helicity. That's why we like to do simulations of turbulence and not random noise against a shock, which is very, very different, I would say.
And while Bill sets up, Sylvia, one quick question.
Yes, just a curiosity. If you go back to the slide with the course rate terms, yes, okay, so you can see, of course, no, that one. You can see in the middle panel, of course, the regions of acceleration and deceleration in particles trapped within the structure, but how this would affect the shock acceleration?
Oh, we don't. Oh, this is a $1 billion question because you can measure it. Actually, I think it's decreasing the shock. The shock is slowing down because of turbulence. You can imagine that, right? It's a turbulent field and something goes fast. Then it starts to, like your car when you drive, right? So we kind of measure it a little bit. We don't have a quantitative measure of this. We have like a looking by eye. The shock was going slower without turbulence, right?
Let's thank Sergio again. And now we come to the last talk of the... Who's this? This is Sergio. Of the pre-coffee break session. This is my should work.
Okay.
We're talking about entropy and dissipation.
I wanted to take 1 second and put this report from 1954 up here by Ribner. This is actually referenced in the Zank paper, but this is the beginning of understanding the relationship between when turbulence interacts with shocks from pre-NASA days. It's a 1954 report. But I wasn't going to talk about that. I just was inspired by Sergio's dynamic presentation to just throw that up there. So, where's the big stick here? I think I'm only going to show one slide with new results in this talk. My main purpose is to get you worried about some things. Because you should be, whenever you talk about entropy and dissipation, you should be worried about very, very fundamental things. So that's what I want to do, is get you worried. Okay, so, well, you know this. That's why we're here. Space plasmas are often called collisionless. Actually, they're weakly collisional, but we approximate them with a set of equations that has no collisions at all. And people talk about Vlasov equation conserves this strange quantity average of f log f, and people call it the entropy, but it is an entropy, but I don't think it's really very relevant to anything. And people also talk about the need to have collisions in order to have like actual dissipation, and I think that's not really a very relevant concept either. But people also talk about effective collisions from wave-particle interactions or turbulence or phase-space mixing and things. And that probably is a relevant concept, and I'm going to show one slide of new results that bears on that. So I'm going to address some of these concerns. But again, my main purpose is to get you worried. So first of all, let's talk a little bit about entropy in collisionless plasmas. To do that, let's go all the way back to thermodynamics. This is now undergrad stuff. Clausius entropy is some function of energy, particles, and volume. And you write down the laws of thermodynamics, and you have ds is dq over t, where q is the heat. And you end up with a second law that says for an isolated system in equilibrium, described by some parameters m, if you have a change of a change from one set of parameters m to n prime under appropriately isolated conditions, you can show that the entropy in the new state is greater than the entropy in the old state, or equal. Okay, that's for a uniform, single, entire isolated system. But if you introduce the idea of local equilibrium, then you can say that the total entropy of the system in LTE is the sum of the little boxes that contain an entropy density now. And the entropy density is slightly different from this functional form from the original one, because now it depends on the number of particles in that little box, but it depends on E prime, not E. And E prime is the total energy density minus the flow kinetic energy at that point. And yeah, then that turns out to be important because, of course, if it was a uniform flow, then you wouldn't worry about it too much. But if the flow is not uniform, then you might have turbulence, and then you should worry about the fact that the LTE entropy doesn't include the turbulent flow at all. And it's a quote from this great paper by Goldstein and Leibowitz, is that, the quote, "The mechanical energy associated with U of x does not contribute to the entropy until it's dissipated." I mean, that should get you to start thinking, because what we're interested in, a lot of the work that we're doing in space plasmas, is what causes the dissipation. But if the entropy doesn't involve the flow and you can't, and it doesn't enter until it is dissipated, then it's not going to tell us anything about what we're interested in. So you should be worried, start to be worried. Okay, now we go to maybe last year undergraduate or maybe graduate school, and we learn about Boltzmann, and you count microstates, and the triumph of Boltzmann's work was to prove that they have an entropy that is proportional to the log of the number of microstates, phase space volume, 6n dimensions. If you have particles, and if it's a uniform equilibrium, going back to the first case on the previous slide, then the parameters are associated with, if they're associated with equilibrium, global equilibrium, then you can show that the Boltzmann entropy is equal to the thermodynamic entropy. And that's really a massive accomplishment in theoretical physics due to Boltzmann. And it's in all the elementary textbooks on stat mech, of course. It almost seems to be the thing that makes stat mech worth doing, right, is the fact that those agree. Well, now if you go to a non-uniform microstate, like we did before, so you coarse grain, you define a particle phase space density, and then you can start calling this Boltzmann entropy is like a gas entropy, and in that case, you can evaluate it in terms of this coarse-grained particle distribution as the integral over everything of f log f, thus the association with entropy in the case of the Vlasov. So this is actually a Boltzmann's H function, and if you add collisions, you can show that it increases. If you maximize this entropy by any process whatsoever, then you find that you achieve a Maxwellian distribution for the microstates. You guys know all this stuff. I'm just reminding you. But the one thing that I said that maybe you hadn't thought about before was the fact that none of this includes the turbulence. So all of these nice theorems that say that these coincide don't know anything about turbulence. So, okay, I mentioned the H theorems. So you have H theorems that says that if you have Boltzmann collisions or other collision operators, that the H function increases. Its target is the equilibrium distribution. And in fact, if you have a lot of collisions so that you have local thermodynamic equilibrium, then you can do all of this and end up with a way to convert the flow energy into the internal energy, and then you have a quantifiable increase in this total entropy. But as far as I know, and maybe people here, there's some smart people here, maybe people will know of an H theorem that describes turbulence evolution. I know of H theorems in, of analogous theorems for Galerkin approximations to ideal fluids with truncated Fourier spaces, but that's not what we're talking about here. We're talking about real gases. So the question, which I'm not going to answer, is there a most probable states argument that leads to the decay of turbulence? I mean, the way I look at this, the main problem is, you know, the classic problem. You have a container, isolated container, there's a partition in the middle, you put all the gas on the left side, you remove the partition, and stat mech tells you that it's going to populate the other side of the container because there's more microstates there. okay, in a very vague sense, when we do our particle and cell codes, or MHD codes for that, well, particle and cell codes, we put all the energy, or a lot of the energy, into large-scale flows and magnetic fields, and we remove the partition by pushing the button, and we know what happens. Nobody denies that a power law is formed and there's an energy cascade to smaller scales, but what drives that? I mean, it can't be Boltzmann or Clausius entropy as usually formulated, because they don't include the flows. They don't know anything about it. So some people like to put in collisions, and that's a fine thing to do because our plasmas actually do have some collisions. And, but if they're classical collisions, they're reversible too, and it's actually only the collision operators that are irreversible. So actually, that just confuses things more. It really doesn't answer the questions. Now, if everything's reversible, then the issue really is what the recurrence times are, and this gets to be almost philosophical, but we know that for systems with many degrees of freedom, the recurrence times, in other words, the actual meaning to reversibility, becomes so large that it's essentially meaningless. Yes, sir?
But any plasma instability really makes this recurrence time immediate. Any pressure and isotropy instability, anything is like reversing the energy from the particles to the field, right? Any kind of plasma instability, unless you want to say that plasma instabilities do not exist, then fine.
Well,
You have to take into account also a possibility that there are fast timescales instabilities that are very active in the plasma, and this is as a short recurrence time. No?
I don't know if I would call that a recurrence time. Do you think it actually goes back to the initial state exactly? I don't think so.
We are taking terms from statistical mechanics, they bring it to the plasma physics. Now I'm doing the same, right? How should we call it?
Well, I mean, like, that doesn't get around the fact that for your plasma instability, whether there's a flow or not, the classical entropies don't include it. So however you explain that, you're not going to explain it with.
About the entropy.
Well, that's what this was about.
I'm about the recurrence.
Yeah. I also know that people can have plasma echoes and stuff like that. And what you've done basically is trim down the number of degrees of freedom so that you can see a short recurrence time. But as soon as it starts to couple to like billions of degrees of freedom, that's not going to happen. At least not for 10 to the 100,000th years or something like that. So, I mean, that number is actually 10 to the 180,000 seconds is a number actually in a stat mech book that I saw. Imagine what that number means. It's impossible. But yeah, if you trim down to like, so you have a spring, the spring returns, but it has like 1 degree, 2 degrees of freedom or something, right? So anyway, just to make that point, in case you don't believe me that classical systems are, I'll appeal to authority. This is a quote from Einstein's autobiographical notes, in which he says, seen from the molecular mechanical point of view, however, all courses of events are reversible. And you know, but the answer, the question is really, so what? So here's my little thought experiment from our paper a couple of years ago, which I'm not claiming answers all the questions, but it further, I think, further clarifies some of the questions. So the text here is basically what I'm going to say. I'm not going to sit here and read it. But basically, we imagine that we have a perfect particle and cell code, like one of Luca Franci's codes. It's perfect, a perfect code. It has an infinite number of particles per cell. It's basically a perfectly accurate solution to the Vlasov-Maxwell system. And that's why this is a thought experiment, not like a real experiment, okay? So you have that, and you start here at time t is equal to 0 with some turbulence energy that everybody who simulates turbulence knows what to do. You put the modes in an annulus in K-space at the large scales. You turn it on, and what happens? Does anybody doubt that the turbulence energy would decrease in favor of the internal energy? I mean, we'll come back to the numerical issue in a minute, but I think most people by this time, now that it's been done by so many people in so many groups, everybody would understand that the turbulence energy is going to degenerate into, with an associated and equivalent increase in the internal energy. But meanwhile, since we have a perfect code, we know that F log F integrated over the system is exactly constant. So this is what I was talking about in the first part of the talk here, is that this number doesn't explain why this blue curve goes down. And that's what we're trying to understand, why the blue curve goes down and the red curve goes up. Now, we imagine that after some time, it might be a really long time, I don't know, you've reached some temperature, kinetic temperature, T1. This is not an equilibrium temperature, because we know that the equilibrium entropy is a function only of the temperature. The temperature's changed, but the entropy hasn't. Okay, so after this time T1, there isn't any more turbulence energy left, or it's down to such a low level that it's like a 0-point level. You can't pull it out. Now, I'm going to turn on some kind of collisions. Now, we know what the temperature was just by conservation of energy, because all the turbulence energy is gone, and it's all in heat now, or random motions. So now we have collisions. The collisions conserve energy, so that temperature must stay constant. I think it has to be uniform because the spatial fluctuations are gone. Although you could ask about heat conduction and things like that. I think that's a subtlety. It would be interesting to see if there's a difference in what happens if you work this out in the two cases. But I'm imagining, I think that the turbulence energy goes away. Why should what? Well, just because the turbulence has, you've waited long. Yeah, well, this is the mean temperature. This is the mean temperature, but I imagine it would probably be uniform because of turbulent diffusion, right? The turbulent diffusion would mix up the temperatures so finely that, but maybe not. Maybe there would be some small fluctuations. It's a thought experiment. I haven't, because it's a thought experiment. Yeah, you keep thinking. It's good. It's good to think about thought experiments, right? Yeah, okay, so anyway, in the end, the collisions can't change the energy, so we know that the temperature stays constant, and at the end, you still have temperature T1, but now the entropy is maximized, and now the Boltzmann and now the Clausius-Boltzmann equivalence holds, and you've reached a global state where they're all associated with one another. But this first part isn't accounted for by the entropy. So anyway, what's the correct entropy? I think that this thought experiment and the lack of equivalence between Clausius and Boltzmann kind of tells you that we don't know the entropy functional for turbulence. We would like to know it. So again, this is a charge to the youth in our group to figure out what the correct entropy functional is. You're still young enough to do it, Daniel. Does it matter? How should we define dissipation? Okay, I only have like a minute, but I told you I was going to only show you one new result. So anyway, I should just mention that all of what I just said is kind of orthogonal to this observation by Montgomery and Nielsen in '69, that if you have finite particle number in a PIC code, it acts like collisions. But that's further complications in all this. Our thought experiment was for Lucas code that has no numerical errors in it at all. So anyway, but that paper by Montgomery and Nielsen in '69 is worthwhile. I was going to introduce pi d, but everybody already has. Thank you for doing that. I'm not going to go through and, well, the point is that I think the reason why people didn't look at pressure-strain interaction for dissipation for a long time is because you could neither compute it, because the codes weren't good enough until, say, about 10 years ago, nor could you measure it, which you couldn't do until MMS. Now we have both, so we can actually do stuff about that. But the interesting thing is, if you do Chapman-Enskog theory for a collisionless gas, the dissipation is still pi d. It's just that you approximate pi by a number times the rate of strain tensor. And then you plug it back in and you get gas dynamic dissipation. We don't have that in the collisionless case, but we can measure pi, so we can find out what's going on. And I'm not going to bother you with all of that. We have codes that conserve energy. That was shown earlier. If you do conditional statistics on J dot E and see how the global average of J dot E in a simulation depends on J, if that turns out to be proportional to J, then effectively you have an Ohm's law, right? That's kind of elementary. Similarly, if you measure, if you have a viscous closure, then pi is constant times d, and you end up these conditional statistics being proportional to viscosity times d squared. But there's no reason for that to be the case in a collisionless plasma, or is there? And this is my one slide I'm going to show. This is a compendium of some 3D PIC simulations from VPIC, some 2D from P3D by Tulsi's runs, and some MMS observations. I think there's about 25 intervals in here. And here we have, this is just the viscous-like scaling. If you do conditional statistics of pi d electron on the second invariant of the rate of strain tensor for the electrons, you find that it scales like d squared. And if you, at least to this level of approximation, if you do the same thing for the proton pi d and condition it on the second invariant of the proton rate of strain tensor, again, you find out that for 3D PIC, 2D PIC, and MMS intervals, parameters are all over the place here. There's no control of parameters. So there's a lot of scatter. I'm not saying that the points would lie exactly on these lines if we did control the parameters. I'm just saying that I think this is interesting because this is, yeah. Yeah, it's the symmetric rate of strain tensor, and this is the square root of the square of that tensor. It's the strength of the shear. So if it were, on the previous slide, I showed that if it were viscous, it would scale like d squared. And you see how close it is for the simulations and the two kinds of simulations and MMS data. So I think we don't have an explanation for this. It's not collisionless. I mean, it's not collisional, but it seems to be effectively viscous as a sum of all of the wave-particle interactions that are going on. Somehow, to our surprise, and I hope to yours, ends up scaling this way. Because I don't have an answer for why this is the case. Maybe it doesn't always happen, but there's a lot of different data here, different simulations, different parameters, MMS data. So interesting, I think. I hope I made you think a little bit about things. Anyway, I'm not going to give the rest of it. That's all I'm going to say.
Right, Total.
Regarding entropy, in case of Boltzmann statistics and collisions, we had short-range interactions. And now the pressure strain interaction can introduce effective collisions, but because the PID is working over different scales, maybe this is not short-range interaction, but some longer scale interaction, which can have a different entropy. Is it so?
Yeah, well, you say they can have a different entropy? What was the last sentence?
For long-range interactions.
Yeah, but I would like to see what that functional is. I mean, if there's an entropy that drives this process, and if there's a way to understand why you have this effective viscosity, I would like to see it worked out. I mean,
Yeah.
ideas like short range, long range, and so on need to be exploited to look into this, I guess.
Right.
Just a comment about
Yeah, no.
the
Oh.
just a comment, a reflection, a thought about the ideal experiment that you have in mind. If you make the correlation between entropy and the conservation of the Boltzmann term, okay, F log F.
Yeah.
Okay. You can be a little bit confused because in the first part where there are no collision, actually you are working probably in distribution functions which are not locally in LTE.
Absolutely.
So you are a different degree of freedom that you have to, which cannot be described by the local distribution function.
Right. That's ultimately a restatement.
And this is the reversibility that you see in the first part. In the second part is the reversibility that usually is in gas dynamics. That's my is a thought.
No, I think you're absolutely right. I mean, that's why Goldstein and Leibowitz say that when you have
But
inhomogeneous.
there you have to describe the global system, including the fact that you have gradients in the system.
Right. So I
Is
wrote
the reason
I
why
wrote F log F.
Chicho asked me where you are temperature gradient inside during the first phases.
Yeah.
Even if you are diffusing in the turbulent space, exponentially, so small that so you are creating gradient in temperature even if you don't see in simulation.
Yeah. Yeah, but this is a statement.
That collision will spread out.
Yeah.
And all the system will become with only one Maxwellian and only one temperature.
Yeah. Well, presumably, if you knew the correct.
But the first part is unknown.
What's that?
The first part you are saying is really unknown.
It's unknown. That's the point of it. The only point of the second part of the experiment is to show you what we should have been able to say about the first one, because ultimately this correspondence should occur. But without collisions, this is the only thing we know how to write down, and it's constant. But I think it doesn't have anything to do with the fact that the cascade is going to form. So
It is not, as you say, it's not the entity.
it's not the correct entropy. So we have some, as a collective community, we have some thinking to do.
Is
One
there
last-
an entropy?
What's
Is there
that?
an entropy? Does an entropy exist?
Does it exist? Well, maybe it doesn't. Maybe there is no stat meant for turbulence. I don't know.
Maybe one last question before the coffee break, because it's getting philosophical.
We
So
can
it's good for a coffee
well,
break.
that was the whole point.
Just a comment. I think the kinetic system is not really modeled well with a blast because you have higher moments.
Yeah.
And there are some papers which have shown that if you go to higher moments, you have something like an H theory in the kinetics. Now, it seems that peak methods approximate better. To some degree, these higher moments, it's actually because you are using a limited number of particles.
Well, at least in the thought experiment, the number of particles is infinite.
Yeah,
And
but when you have the loss of system, and there the entropy is constant, but if you go to real kinetics, loss of system is only the zeroth moment.
okay, well, first of all, if you have a kinetic system, then by definition you have closed at the single particle distribution function level, and there isn't anything else in the BBTKY hierarchy. So, but I mean, Boltzmann is actually what we used to call a kludge, right? Boltzmann is like saying, well, we don't know what's happening, let's pretend we can do it with the single particle distribution. Because you don't have collisions if you don't have a correlation between particles, right? So Boltzmann is a kind of a fake anyway, the Boltzmann collision operator. The Boltzmann entropy theorems are profound, but the collision operator is useful, but fake, I would say. So anyway, I agree with you that the whole hierarchy might have totally different properties than the Vlasov equation. But we're talking about solving the Vlasov equation, right?
But suppose it solves the loss of equation because it has a limited number of particles, and you have some force training within the formulation volume.
That's right, but in the limit of the large number of particles, those effects in principle go away. In fact, that's the Montgomery paper shows that the effects are there and also shows that they decrease as you increase the number of particles.
Okay, all right. I think we have to go to the coffee break. Let's be back at 20 past to start on time at 20 past. At first, thank Bill and all the other speakers of this morning's session.
Yes, absolutely. Yeah, as a well. No, it's absolutely.
It's hard to follow.
Oh my goodness, yeah, you have to slow it down.
ledges on the show. Ho preso il logo della conferenza. È colpa loro. Cambiate. O cambiate il logo della conferenza. Okay, welcome back everyone to the second part of the morning session. And we'll begin with Tommaso Alberti, who's talking about hypersolar probe and MHD field. Reconciling.
Thank you, Daniel. Okay, good morning to everyone. Yes, this is a talk based on a publication that should appear soon on the Astrophysical Journal Letters. And it is mainly based on some observations by Parker Solar Probe and try to reconcile with some MHD theoretical findings. This is because since the launch by Parker Solar Probe, we have more data at higher resolution, both for plasma and magnetic field, through the inner heliosphere, and we can reach distance close to the sun as never reached before. What is interesting is that since the beginning of having data by Parker Solar Probe, for example, there has been a huge interest in investigating the properties of turbulence, and in particular, the first work by Chris Chen showed that there is a changes from a Kolmogorov-like slope to a Kraichner-like close to the sun. So there is a radial dependence of the spectral slope of turbulence. And we also show that there is a radial dependence of the intermittency properties, but also there are many studies on turbulence, both in situ and also on the radial behavior. These are, I think, a partial list. There are surely more and more on this topic. So the main question is that we have some observations. In particular, the first one is that Chen showed that we have changes from a slope to -5/3 to -3/2 when approaching the sun, and this is related to not only the Elsasser variables but also to the magnetic field and the velocity field. The second one is the power of Elsasser variance, so the variance of zeta plus minus is decreasing for zeta plus when we move away from the sun, while is almost constant more or less for the inward propagating components. And what is interesting is that close to the sun we have an unbalanced scenario where zeta plus is much higher than zeta minus in terms of variance, while far away, more or less close to 0.6 astronomical units, the two fields become almost equal in terms of variance. There are also other facts, for example, that some scales, such as the outer scales or the higher inertial length or the correlation scales, evolve with radial distance. This is an interesting plot by Chen, who demonstrated that there is a dependence of the radial distance of the correlation length, but also this is a recent paper by Manuel Cuesta and Bill and co-authors, where shown that also the ion inertial length evolve as a function of the radial distance collecting not only PSP but also Helios and Voyager. And what is interesting is that typically the inward propagating modes have a longer correlation times than the outer one. So another interesting property is also shown in this paper by Manuel Cuesta is that the Reynolds number and also the intermittence, as we shown before, is evolving with the radial distance. So we have some facts that suggest that we have a radial evolution of the fields. So these facts can have some consequences. Starting from the first one, the case one is that at larger heliocentric distances, we have that the variance of zeta plus and zeta minus is almost the same. So if we develop this equality, we have a close relation. That means that the dot product between the velocity fluctuating component and the magnetic field fluctuating component must be close to 0. So this means that they should evolve on orthogonal planes or directions. If we check the other relations when we are close to the sun, this means that we have this inequality that in principle is satisfied for any angle that is different from 90 degrees and that is maximized when the two fields are parallel. So in the first case, so far away from the sun, we have a restrictive condition on the fluctuating components of the velocity and magnetic field, while close to the sun we have no clear relations. But if we look this in a different way, so if we define the cross-helicity and the residual energy, as usual, the cross-helicity takes into account the balance between outward and inward fluctuating component, while the residual energy is the balance between kinetic and magnetic energy. The first case, so far away from the sun, since the dot product is 0, this means that the cross-helicity must be 0. While the second case, where the zeta plus is much higher than zeta minus, easily allows us to simplify zeta minus and have that sigma c must be close to 1. So these two scenarios are the two scenarios that we would like to test with PSP observations that can be relied on some MHD invariants and yes. Yes, exactly. Yes, yes, indeed. And indeed, what I would like to yeah, no. What I would like also to highlight is that the two cases can be obtained with strict or some fixed relation for the cross-helicity, but not for the residual energy. And this is important because this is what we observe indeed. So, yeah. Yes.
But there's a difference, right? I mean, the red boxes have a different meaning if there's a bracket around them or if it's
yes,
point-wise.
exactly.
And you don't see the top case point-wise really ever.
Exactly. Yeah, indeed. Indeed, when we make this some kind in the next, we make some averages within the inertial range to assess this in the MHD inertial range. Yes, sure, Bill, you are right. This is not point-wise, but this is on average, statistically. Indeed, this has a consequence because we have some issues on the data also. So, in principle, we have two scenarios that can be characterized via the cross-helicity, but not unambiguously with the residual energy. And this can be also drawn recently by the nearly incompressible MHD model by Gary Zank and also Adhikari. And this is the results of the model who show that there is a decreasing pattern of the cross-helicity as the heliocentric distance increases. So we would like to test if these two scenarios can be found in the Parker solar probe data. So what we did is this one. We used the magnetic field and plasma measurements from Parker solar probe. We used 7 perihelia from encounters 5 to 11. We have different resolutions, so we homogenize by resampling at 1 minute resolution, covering 0.1, 0.85 astronomical units. Unfortunately, on plasma data, you can see that there are some gaps, so only the 15% of points can be used. And another thing is that the majority of points belong to encounters 5, 6, 7, and 11. But this is not important because our approach is statistically, so we have not comparing one encounters with the other one, so not point-wise, but on average and statistically. And the first thing that we investigate was the radial behavior of the helicity and the residual energy. And as you can see, there is a decreasing pattern of the cross helicity from 0.6 close to the sun up to 0 far away. So it seems that this is quite matching our observation with sigma c close to 0, while there is no exactly matching with the prediction of having sigma c close to 1. And the second important thing is that the residual energy is almost constant. And this is in agreement with also recent findings by Siulas and Andres, and also qualitative agreement with the, in terms of the cross helicity with the nearly incompressible model, but not in terms of the residual energy. This in the next one, yes. This is all solar wind cases, so there is no distinction. And so, yes.
All of the stuff that you wrote in the upper left-hand corner is right, but it was all well known in the early 1990s.
Yeah, exactly. Yeah, exactly, indeed.
You don't have to just reference things from the last 2 years.
Yeah, but this is also for matching solar point. Indeed, I also referred to your publication with Manuel Cuesta, who also used it, but also before with Bavasan and the other one. Yeah. Yeah. So the framework that we have is that we have some kind of prevailing two-dimensional structure over the slab component when we go away from the sun. This could be linked with the geometry between the large-scale solar wind field and the magnetic field, because when we are close to the sun, the flow is most radial, so PSP can measure prevalently slab components, while when we move away, the flow is not radial and we have the predominance of a two-dimensional component. To go a bit deeper, we make some kind of plots that have been shown with Helios, for example, has been suggested before, in terms of the joint distribution of the value of the cross helicity and the residual energy. This is close to the sun, so in the range 0.1, 0.3, and this is far away, 0.6, 0.8 astronomical units. What is interesting is that here we have two bumps. One, when we have sigma C1 and sigma R0, that seems to suggest that we have an outward Alfvénic fluctuations with equiparted energy, while we have another bump of probability here, where we have some kind of non-Alfvénic fluctuation with an excess of magnetic energy because the residual energy is negative. But what is interesting is that when we move far away, we have also the probability of observing some kind of negative cross helicity. This means that we can have some kind of inward. Yeah. Yeah, exactly. These are very in agreement with Robert. The main problem is that they used the Helios data or release, I don't remember, up to 0.29. So this is a bit close to the sun in this step, but far away we are in agreement. Perfect.
Also a lot of work by Marsh and Chuan Yi too.
Yeah. Yeah. Exactly. Yeah. And what is interesting is that far away from the sun, there is at least no statistical evidence of only inward and outward modes, although you know very well that we can find some kind of Alfvénic streams also far away from the sun. But statistically, the grid population is this one. And another important thing is that so it seems to suggest that we have some kind of evolution of turbulence from a more Alfvénic to a less Alfvénic behavior, always in an excess of magnetic energy, and this has been also shown by, for example, Roberto and Marsh with Helios and before. And what is interesting is that here we know the emergence of a null probability of observing negative cross helicity. So this can be related to the occurrence of inward fluctuations. So this can be related to the fact that if we have the nonlinear term that becomes relevant as we move away from the sun, we can generate some kind of inward propagating modes because we have an excess of outward propagating mode. And also Bill shown this one, at least theoretical in this case. And the other analysis we made, as Cicemalara was saying before, is to separate the fast and the slow solar wind. What is interesting is that you can see that the fast solar wind here moves from more or less probability close to 1 to have sigma c 1 and sigma r 0 to a different situation that is almost the same as observed in the full time series, but also with an emergence of inward fluctuations. The main problem is that during this year, the most of the solar wind was slow solar wind. So the number of data points corresponding to fast solar wind is not so large. But there is a clear difference, not particularly evident far away from the sun, because we always have some kind of non-aphelic fluctuations about inward and outward component, but in particular close to the sun, because the fast solar wind is characterized more or less by the monostate behavior. And this is also recently in agreement with some papers where the nearly incompressible MHD model has been applied to Parker-Sutterprop data, but also with previous observation. So, yeah.
We keep stopping you about references, but the comparison of the fast and slow wind and the degradation of the cross-helicity in both of them can be described by the same set of equations that was Ben Breach's PhD in 2006, 2007.
Yeah.
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 And the Zank explanation is the same.
Yeah, exactly.
In fact, they're using Breach's equations more or less.
Yeah, indeed, exactly. This is the case, and also this is the evolution of the correlation length, for example. This is the case. So, as a short summary before another conclusion is that, okay, we have some kind of evidence of having an MHD alpha-Phoenix scenario close to the sun, and far away we have more or less equipartitioned energy with a Kolmogorov-like behavior. There is an earlier paper by Dobrovolny, Mengenet, and Belty who shown that if you have an initially asymmetric state as close to the sun, this should relax in principle, towards a static state where we have only one mode. So if we have zeta plus larger than zeta minus close to the sun, in the end we should have only zeta plus. This is not the case, because in our observation we have zeta plus and zeta minus, and this means that we have, our main result is that the final state is not only not characterized by the absence of one of the two modes, but on a different degree of correlation between the velocity and the magnetic fluctuating component. So what we try to do as a last slide, this is one. The key term is the nonlinear term. So if we use the nonlinear term can be written in this case. We have some kind of energetic contribution because this is b squared, and this is some kind of cross-coupling. If you assume the incompressibility, the cross-coupling term can be written in this case. And this traduces into two additional considerations on the two scenarios presented before. So our idea is that there could be a term, an additional term in the nonlinear term that becomes important as we move away from the sun, and this could be related to the fact of having cross-coupling between fluctuating components and also belonging to the inertial range, having some effects on the cascade mechanism. And so this could be the reason for which we have close to the sun a Krykman-like behavior, and far away Kolmogorov-like behavior. But this needs to be tested to see if this is exactly the case. But it seems that an additional term emerges, and this could change the scaling property. And I thank you for your attention. This is the paper, if you are interested.
It's a good question. Of course, now only one piece of the puzzle is missing about the magnetic helicity pollution. So
Yeah.
we can do a plot of this reduces cross magnetic to match with when you go to the sun. Will be something.
Indeed, the cross-coupling is something that is related to the cross-helicity or such a way. Yeah, of course, yeah. Yeah, indeed, one of the conclusions could be that the helical component of turbulence cannot be only transport the light, but this evolves, and in this case you have that. Yeah, yeah. Right.
I would say that the second thermodynamic curl of V cross B is a consequence of having Z minus E to Z plus. It cannot be the cause. It cannot transfer energy from one piece to the other.
Yeah, exactly. Yeah, yeah, and this is also only valid under if you have incompressibility, of course. This is yeah, but sure, this is a missing point. So at a first glance, you can see that there is an additional term in the nonlinear term that evolves and can become important. And yeah, 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 yeah. Yeah, yeah.
My explanation is based on the fact of expansion we will know that affects especially low frequency
Yeah,
modes. So Z minus correlation length
yeah, yeah,
in that sense.
yeah,
But the other thing is that when you analyze, especially the PSP data, you may have an effect of analyzing flow that comes from higher latitude, larger distance. So is it
yeah.
a way to mean of statistical analysis to distinguish these two things?
I think at the yeah, I think at the present, no. Likely with solar orbit, where we have some kind of co-rotation, we can have some large time series when we. But yeah, it's difficult. Also, for example, it's difficult to separate fast and slow solar wind for this reason. But I agree with you. Indeed, we cite your research at the end of the paper on that point exactly. So we are in agreement.
Where's the next speaker? Maybe when the next speaker comes down, one more quick question. Yeah?
Well, it's going to be a comment, not a question. So
Perfect.
in the late 80s, Aaron Roberts and others realized that the cross-helicity was decreasing in Helios and in Voyager. And Roland Grapin, my good friend from Loudon, was the first person to realize that that was in contradiction to Anit Pouquet and other people, and also Dobrovolny Mann.
Yeah, yeah, exactly.
And so he gave a lot of talks about this contrast.
Yeah,
A few years later, people realized, both in observations and in theory, that in regions of strong shear, the cross-helicity was going away much faster.
Yeah.
So I agree that you need another coupling, but it's not fluctuation to fluctuation.
Okay.
It's fluctuation to large-scale.
Okay. Yeah.
And this is the basis of the so-called turbulence-driven coronal model,
Yeah.
too, is that you produce reflections. And it's basically a generalized reflection.
Yeah, 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 yeah.
There's a lot of literature on that. I can send you 20 or
Yeah,
30.
sure, yeah, yeah. Yeah, but indeed, I agree with you. Indeed, our conclusion is that the Dobrovolny picture is not valid because this is a restricted case and only for particular static and stationary case that is not observed in the data. Yeah, sure, I agree. Yeah, thank you.
Thanks to Tommaso again. Thank you very much.
Thank
We'll
you.
come to the next talk by Vincent David about the zero flow of turbulence. Yeah.
Okay. So good morning, everybody. I'm Vincent David, a third-year PhD student under the supervision of Sébastien Galtier and Fouad Sahraoui. And today I will present two topics, and I'll try to make a link between the two. So firstly, I will speak about the zero flow of MHD, and then I will move on the solar wind and speak about the energy transfer. So to start, beginning with the very basics. So we all know that the energy cascades through scales, and we have what we call the zero flow of turbulence, which states that if in an experiment on turbulent flow, all control parameters are fixed, except for the viscosity and the resistivity if we work with plasma, which are lowered as much as possible, then the energy dissipation tends to a non-zero limit. And if we write down this statement as an equation, we obtain this one. And here I'm interested in the epsilon value. So how can we derive an equation to calculate this value without pass to via the derivative of the energy? So to do so, I will focus on what we call weak solution. So a weak solution is a solution that does not remain smooth after an arbitrarily long time. But I have to introduce another mathematical concept because there is something strange in this definition. What does remain smooth mean? So to fix this issue, we have to introduce the Holder continuity equation, condition, sorry, which is just a generalization of the Lipschitz one. So here we have a parameter alpha. Where is the stick? And for the Lipschitz condition, it's just 1. So for the rest of this part, I will just focus on the Euler equation because all the essence of my problem is contained in its equation. So we arrive with the conjecture, the Onsager conjecture that states that if the Holder exponent alpha is less or equal to 1/3, then the weak solution for the Euler equation and for the MHD2 do not obey to energy conservation. So if we can draw this statement, and geometrically, if we consider a velocity field with a sharp gradient, and we scan for every point, we can look at if this point verifies the Holder conjecture. So for this one, it's okay because the neighborhood of this point belongs to the gray area. But if we take the middle of the gradient, the inflection point, it's not the case. So we do not verify the Holder, the Onsager conjecture. And then this type of flow do not conserve the energy if we consider weak solution.
Sorry, I missed what are the blue and the gray curves?
The blue curve is the velocity field curve, and the gray curve is the boundary of the domain that verify the Holder condition with the parameter alpha is equal to 1/3. Okay. So to fix this, okay?
Can you clarify what you mean by not conserving energy? You mean that the cascaded energy doesn't agree with the dissipated energy?
Yes, it's the next slide. So if we consider weak solution, we can in fact convolve the film to smooth them. So we convolve with a test function phi, which has a width sigma. And the idea is to smooth the field, compute the derivative, and then take the limit where sigma tends to 0 and the test function tends to a Dirac distribution. So doing so, we take the first classical Euler equation in the one end. In the other hand, we take the smoothed one, and we build an energy conservation equation. And here we do not have any dissipative term. But if we consider weak solution, there is another term which appears. And this term, we have an analytical formula which...
So just a comment. So if the Euler equation is producing a singularity, then the nonlinear term is producing energy.
Yes, exactly, yes.
That's the conjecture.
And so you can, in fact, you can see this with this formula, which is the limit when we tend to...
No,
so.
this is incompressible. Fully. There is a theorem on this by Kuhn.
Energy is still conserved, right? I mean, it's just not conserved by that equation.
Yes, physically, yes. But mathematically, in fact, we have this particularity if we consider weak solution. And this brings me to this equation I will use after. Because, in fact, it's the local version of the K41 law. We have the limit when sigma tends to 0 of the convolution product between the test function and the third order structure function, which is the same as the one in the K41 law. So here we do not need to perform a statistical average to express the epsilon value. We can measure it at each point of the data. Yes, because when you... Yes, yes. Up. Okay, so we can go a little bit further in theory if, depending on the type of flow we are looking at. So if we work with the discontinuities and the delta U increment is just a constant jump and constant value, so the dissipative term scales like sigma minus 1. If the flow, we work with turbulent fluctuations and the flow obeys to the K41 law, and we have a flat power law. And finally, if we work with viscous flow, we can perform a Taylor expansion on the delta U, and we obtain a sigma squared curve. And we can define the Kolmogorov scale as a transition between one type of flow and the viscous one. So to summarize this part, we have a theoretical tool who seems correspond to the epsilon involved in the zeroth law of turbulence, and its behavior depends on the nature of the signal. So now I will move on the energy transfer in the solar wind. So I'm interested in incompressible MHD equations, and if we consider a weak solution of this set of equations, we one more time can build a local energy balance equation, and we have another dissipative term, which is in fact the same structure as before, but here we have the same structure function as the Politano-Pouquet law. So we have the local equivalent of the Politano-Pouquet law that does not require any statistical average. We can measure the energy transfer. Here, because we are in the solar wind, it's not dissipation, it's energy transfer because we are stuck at MHD scales and the energy cascade go far away the energy. So it's just to measure the energy transfer, not the dissipation. No, the two little d's appears here in the viscous and resistive dissipation, but here it's neither viscous nor resistive. And in fact, this structure function is the same as the Politano-Pouquet law, so we have a local equivalent. So now I will apply this quantity on the data. So here is a sample of PSP data. So we have a bunch of discontinuities here for the velocity field. That's the same for the magnetic field. So we cannot apply the exact statistical law on this type of data. And what we observe in the last panel is the inertial dissipation. So we have a very rich description of the energy transfer using this tool. And in fact, we cannot apply the PP98 law because we have discontinuities and we miss a lot of information. So this is a very useful tool I present you. And if we look at carefully to the last plot, we can see that discontinuities give the main transfer to the energy, or the main contribution, sorry, to the energy. Here we are in log plots, so the brighter color are much more intense than the darkest one, sorry. And one question is, what about switchbacks? Because we know PSP detects switchbacks close to the sun, and switchbacks have sharp gradients, so it should contribute a lot to the energy transfer. So here is a sample with 3 switchbacks located on the vertical yellow lines. And what we observe, it's when we are at a fixed time, so here, here, and here, and we look at the evolution of the inertial dissipation as a function of scale, sigma, we obtain a power law in -3/4. So I do not, yes?
Sorry. There is another group working on this, like Lucas Orriso is working on local transfer rate,
yeah,
which is the limit. When you send your increments to 0 in your kernel, it becomes exactly the thing he's doing. And I think that the measurement he proposed is exactly this. So maybe on the first,
yes,
on saying first time the solar wind is a bit too much, because already there is a measure like this in the locality. And they are equivalent from the Dungeon and Robert point of view. If you're sending your kernel to 0, can be demonstrated, is demonstrated.
Yes, it's the MHD equivalent of the Duchamp-Robert work. And I spoke with Luca. In fact, it's what he used is PIV or LPV. I don't know what's the acronym of its tool, but it's very heuristic. It's not mathematically well defined. So here is you can build a theorem with this. It's very strict and rigorous.
Okay,
so
but I won't be surprised if they give the same.
yeah, the result is quite the same. And so if we look at switchbacks, we have this power law that appears, and we cannot explain it theoretically. So if you have an idea, I will be happy. And what we see in the last plot, so the switchbacks give the main contribution, and they have a non-local impact in scale, so we can detect them at high sigma values. So they play a very significant role in the energy transfer. So before to conclude, I wanted to perform a statistical comparison between the inertial dissipation and the epsilon computed with the exact law. And you have here the dashed line, which is the equality between the two. And for PSP data, we have that d high is slightly higher than the epsilon prediction. And this, in fact, is due to the presence of discontinuity because I did not filter the data. So I leave the discontinuity. I left, sorry. And here is a typical example. If we plot DI, we have a flat curve which is well defined, and we can take the mean of the plateau. Here, for epsilon, which is normally we should have a plateau, but it's not the case because of the discontinuity. So here it's well defined, and it works better than the epsilon, which requires statistical average. So to summarize, we have a tool to estimate the local energy transfer. Switchbacks, when they are present, give the main contribution to this energy transfer. And this seems to be characterized by this minus 3/4 power law. But it's still an open question to answer. Why this power law? So to continue, we can add the Hall effect to probe smaller scale or take into account the anisotropy. And explain this power law. So if you have an idea, I'll take. So thank you.
Thanks a lot, Vincent. Questions?
So to be precise,
Yep.
the thing that you were saying behaves like sigma to the minus 3/4 is this d sub I, right? This dissipative term that you
Yes. Yes.
And what is the relationship between that formulation of the dissipation and what you would get just by Germano-style scale filtering? Is it the same thing?
I don't know their work, so I can. No, I don't. Sorry. So
It's just this scale filtered transfer.
as like the coarse graining, no. Or
It's what people do when they do large eddy simulation. You filter the equations and you measure the exact transfer from the resolved scales to the non-resolved
Okay.
scales. And then the guy who invented that stuff is called Germano hydrodynamics.
Oh, okay, but so
It's the same thing.
I don't know their work, so I will read it and I.
Would you
but-
describe what you have done as conceptually equivalent to scale filtering?
Yes, we have a kind of scale filtering because we have to smooth the equation. Take the smooth one, the non-smooth one, to build an energy conservation. So there is a type of smoothing behind this. But to compare with Germano, I can answer. I don't know their work. So,
Looking on this equation, you have gradients, so I don't understand, I missed the point how you apply this equation to the one satellite data when calculation of the gradient is impossible.
technically, it's just a wavelet transform with a derivative of the kernel. But
Saying that this is a 3D integral, really. You have to do it. When you
Ah.
do it 1D surrogate, you are hoping that it's also dropping in the other direction, probably, right? This is when you do it
in 1D, I just have dx or d. Yes.
No, integral is 3D. My question is, the integral is 3D, theoretically.
Yeah.
Because
Yes.
actually our question when Denis Cousin of this main
Mm.
one, so he did this first application of these ideas on the image simulations in 3D, it is working. But when we apply it to the data, we were just what we are doing because we have no with mass attack, we have no, it's impossible to create this integral. So how are we doing?
I just, in fact, technically, I integrate on the time because we have time series. I perform the.
But everything is along the line.
Yes, I suppose the Taylor hypothesis. Yes, I suppose the Taylor hypothesis too.
What is Luca is doing then? So it's exactly the same. No?
In practice, it's.
No, but so it's then exactly equivalent to what is Luca is doing. Because
No, we really have to do it 3D. That is doing, you can do it only 1D, but
Yes,
that's
I can.
your assumption.
Yes.
You pray
Yeah.
that it's happening the same
Yes,
in the other.
because with the data I can do differently. I assume the Taylor hypothesis and I just have 1D because I have time series. So I prefer do this rather than.
Current way that we are traveling toward your direction. You see strong gradient, but you don't know if there's energy transfer in that direction.
No, I just have the time series, so I assume this 1D.
You measure some kind of precision.
What?
You're looking, just because you're looking only in one direction, so the system.
No, in fact, I looked to the 3 coordinates available.
Only
But there is, yes. Yes, of course.
I think there was one more question there. Yeah.
Yep.
Did you check whether your results that you find that switchbacks are consistent, similar with what you would find on just discontinuities?
I don't think I captured your question. What's the difference between?
Dissipation that you found
Yes.
switchbacks. Did you check whether it's similar to the dissipation you can find general?
I compared the two, and the switchbacks gives a higher dissipation rate, but it's only due to the gradients, which because here we computed the increments of velocity and magnetic field. So because we have sharp gradient, we have an energy transfer. That's the theory. So if we have discontinuities or switchbacks, I just can measure the energy transfer. I cannot distinguish and diagnose. No, I cannot diagnose. Just I can compute and estimate this. Okay. Thank you.
All right, let's thank Vincent again. We'll come to the next talk, which is by Luca Franchi, about his perfect simulations.
I'm ready.
You ready?
Yes.
Manuela was ready? Also ready. Great.
Okay, so good morning. So thanks, Bill, for increasing the expectations of my simulations. No pressure. I just felt like I had to change my title. So basically, the scientific rationale for my work is the same as for my previous talks here. So basically, we are trying to understand what's going on around the ion and the electron kinetic scales in the transition region, at ion scales and down below, because we want to understand the processes for energy dissipation and particle heating in the solar wind. What we are doing is running perfect numerical simulations, which we use to provide key additional information that is not available from 1.1 spacecraft measurements. And we try to model spacecraft observations and to compare with spacecraft measurements. So these are a 2D and a 3D hybrid simulations, so where the ions are treated kinetically and the electrons are treated as a massless fluid, from a couple of years ago, where I was trying to model this steep transition region just around the ion scales, which was observed by PSP during the first perihelion. So what I did was analyzing the PSP data in the first perihelion, compute the power spectrum of the magnetic field, and try to run hybrid simulations using some parameters which were basically set to average values measured by PSP. And basically what we got is a very good agreement for the power spectrum of the magnetic field between the simulation and the observation. So basically, what we thought is, why don't we try to go even farther and try and basically to predict what a spacecraft would measure if it was able to go down to the electron scales. So we ran fully kinetic simulations, in this case, using a few thousand particles per cell to reduce the noise. And so here you can see the magnetic and current structures at the time when turbulence is fully developed. So you see lots of vortices, filamentary structures with a size comparable to the ion inertial length, and very thin and strong current sheets with a width which is comparable to the electron inertial length. And we also compare the power spectra between the hybrid simulation and the fully kinetic simulation, because of course in the case of the fully kinetic simulation, we need to employ a smaller grid to increase the resolution. So we just wanted to double check that in the range of scales where the two models are supposed to hold, because we don't expect electron kinetic physics, the results were comparable. So you see quite a good agreement. So here there is a small difference in the magnetic field, because here we have the injection scale for the fully kinetic simulations. But in general, there's quite a good agreement for the spectra, the power spectra of all the fields, until basically we approach the electron scales. So basically this is a further confirmation that until we reach electron kinetic scales, the hybrid model, considering electrons just as a fluid, is a good approximation. And we're able to reproduce the dominant processes. So we also analyzed magnetic reconnection events. So we identified X points, so saddle points, computing the out-of-plane vector potential. So these are potential reconnection sites. And then we computed a few quantities which are considered as indicator for magnetic reconnection. In this case here, you see that we use a threshold for the current density to identify the strongest current structures. And you can see that in all these points where we have X points, in many of them, we actually observe very strong current sheets. And these undergo reconnection. You can see some structures like with an X point. Yes?
There are major differences with our results from like 2012 with Blasov codes. I mean, do you see anything novel in this? Or because sometimes when we were doing this, when we were doing some mistakes and doing simulations with parameters, we observed that the current sheets, they break to produce some secondary point, but because of numerics. It appears that now are very nicely coherent.
Yeah,
So
yeah.
And
Yes. And also, so what we did, I'm not showing it here because I don't want it to make it all about spectra, but we are actually able to see pretty good power law spectra even below the. So we double check. We also ran lots of convergence studies on the resolution, the spatial resolution, the number of particles to be sure that what we are observing is not dependent on the noise. And also, we observed the coexistence of standard and electron-only reconnection. So basically, the red shaded areas here are areas with strong electron jets. The blue ones are areas with strong ion jets. So you can see some reconnection events where we observe both. So we have some kind of standard reconnection and areas where we only have electron jets. So these are electron-only reconnection events, as we usually define them. And I think what's really the difference between these two types of reconnection events is basically the length of the current sheet. Because, for example, here, where the vortex, the ion scale vortex is very elongated, so the interacting region here is quite shorter than when basically we have something like this. So in that case, basically, we are we have a reconnection event at scales where the ions are already decoupled from the magnetic field, likely. So we don't drive the ion jet. Anyway, what we also observed is that in correspondence of reconnection events, we also observe electron heating, and especially a very strong electron temperature anisotropy. And this is interesting because if we take the maximum of the current in the simulation box, and we basically use this as a proxy for the time when magnetic reconnection starts occurring, because at the beginning of the simulation, we have the formation of current sheets which are squeezed between vortices, so the maximum value of the current is increasing until the first current sheet basically breaks and reconnects, so we have a drop in the maximum. So basically, you see that the electron temperature is basically more or less constant. The total one, the black line here, is more or less constant until this time, and then it starts to increase slowly. And even the electron temperature anisotropy is slowly decreasing, but then when reconnection starts occurring, this decrease further steepens, yes. So there seems to be a correspondence between the time where reconnection starts occurring and electron heating. What we've also been doing is computing the different contributions to the electric field from the generalized Ohm laws. So here you see the different terms, the MHD term, U cross B, the whole term, the electron pressure term, and the electron inertia terms. So here you can see the different contributions to the power spectrum. So the main point, this is consistent with, for example, observations from MMS, where we actually, thanks to the multi-spacecraft measurements, we can actually compute the gradients, for example, of the electron pressure tensor. So the main point is that electron inertia effects seems to be negligible, but I will get back to this later. So as we expect, the MHD term drops around the ion scales, and the kinetic scales, the main contributions come from the whole term and the electron pressure term. And we are actually able to look at the structures in real space, because it's, of course, a noise-free simulation. So this is the MHD part of the electric field. This is the whole term. We can see very nice thin and strong structures in the whole term, basically in correspondence of X points around vortices. we can see very similar structures in the electron pressure tensor term. And this is the electron inertia terms. And you can see that this is very basically negligible because here the color scale is 2 orders of magnitude smaller. So we see basically structures in the same more or less points as the other terms, especially when we have X points and reconnection events, but these are very small, much smaller, so they don't really provide a big contribution to the electric field. This is related to what Shadi showed this morning. So basically, since I have both the hybrid and the fully kinetic simulations with the same parameters, I can also compare the spectrum of the electric field, which is this black line here. And so these are the different contributions to the generalized law from the hybrid simulations, where we are forced to use an approximation where the electrons are considered isotropic electrons because we have a massless fluid, so we don't have the electron distribution function. So basically, we don't have the full electron pressure tensor. So basically, we end up having the gradient of the isotropic pressure, which we can approximate as basically the gradient of the density times the electron beta.
But in this case, if it's this case, then it's useless, right? Because
what is useless too?
The electron pressure, if you have a scalar, because then you take the curl of that at zero.
Yes, exactly.
You already like graph log n.
Exactly. So this part wouldn't contribute to the magnetic field through Faraday's law. Yeah. So what we do here, so the solid lines are from the hybrid simulations. The dashed ones are from the fully kinetic simulations. So you can see that the whole term and the electron pressure terms are quite well overlapped until we reach the electron gyro radius. So basically, this is a further confirmation that we don't really have significant electron kinetic effects at scales larger than rho e. And this is also the same term computed in the fully kinetic simulations, but instead of computing the divergence of the full electron pressure, just taking this, basically making the approximation of isotropic electrons. So it is this dash dot red line, and you can see that it's more or less similar to what we get from the full electron pressure tensor. So what I'm showing now, it's just preliminary. I've been doing a lot of work on this electric field decomposition, but I prefer to show something preliminary in the spirit of the informal workshop. So I've been saying that the electron inertia terms are negligible, and that's kind of true, but you can see here these kind of structures. This is a zoom, and they only appear in the electric field. They don't appear in the magnetic field. And also, they don't appear in any of these 4 terms that I computed for the decomposition from the generalized Ohm law. So basically, the most reasonable explanation is that this comes from this term here, because when I compute this, unfortunately, so far, I don't have such a very high output rate, which is comparable to the electron scale. So when I compute this term here, basically, I'm averaging out everything that occurs at scales that are comparable or smaller of the electron, to the electron scale. So there is probably a considerable contribution from the displacement current. And this is in agreement with, for example, what Carlos Gonzalez showed a few years ago. So he was seeing this bump in the parallel electric field, and he actually computed this term here. So he was actually finding that this was the reason for this. And why do I think this is important? So here, if you see, this is where I see a very small discrepancies between the sum of the 3 major terms in the electric field and the electric field, which is actually given in output from the fully kinetic code. So if I compute now the parallel electric field, you see that in the parallel electric field to the local magnetic field, actually I see these structures here. So these kind of wave structures. And if I compute the spectrum, the power spectrum of these, the parallel electric field has a bump just here, which is in correspondence where I see this discrepancy here. Sorry? This is the parallel. Here? I really don't know. I think it just comes from the other terms, from the MHD term. Yeah. I think it's the second order. So in the MHD term, we would have also U cross, not just U cross B naught, but also U cross, so delta U perp cross delta B perp. So probably. okay, I'll just finish. Maybe we can go back to this later. So what we did was also running another full peak simulation with all the same parameters, but a much smaller electron beta. And in this case, we see even stronger structures in the electric field which don't appear in the magnetic field. So again these are kind of electrostatic waves. And in this case, the discrepancy between the generalized law, where this is probably underestimated, and the electric field which is given in output by the code is much smaller, much larger. And again here, if we look at the parallel electric field, we see these electrostatic waves. And again, there is this huge bump in this case, which basically explains for this bump in the electric field, which is not captured at the moment from the different terms from the generalized Ohm law. Not yet, no, because this is very preliminary. I've been doing this in the past few days, so there's a lot of work I would like to do on this. Yeah, I can show you something actually about this. So basically, an hypothesis that we could have some kind of bump on tail distribution if we have an electron jet, basically. What we see here, for example, is that as an effect of reconnection events, we have these strong electron jets. So these could maybe give something like this. So these are basically, the good point is we have the electron and ion velocity distribution functions in every point of the simulation domain, which is 2 terabytes of data. So I didn't have time now to go and look exactly in this point. So these are just a couple of electron PDFs that I showed already last year when it was already preliminary, and then I didn't have time to work on this for a full year. But you can see that so this is basically the parallel electron velocity, and you can see that we have this kind of beams, I would say. So here we can imagine that the distribution function could look like something like that. And to conclude, so we can have a look here at a zoom and look at all these nice tiny vortices here. I think it's quite cool. So this is basically, this grid here is of the size of D, so the electron inertial length. So these small vortices are of a size of electron inertial length. This is only possible because we are noise-free. And so this is instead the resolution of the simulation. So this is a zoom, so you can see that they are resolved, so we don't have it's not a numerical effect. And these are evolving very fast in time. So this is 0.5 ion cyclotron times. So for example, this one here has already disappeared. This here is just appearing. So it's, I would say, at electron scale times. And this is a time evolution. I didn't have the time to do the video. But so here we have probably a reconnection event. We have this jet here. And look what happens. So we have the formation of these small vortices. They grow, and then they start interacting and do all of this kind of interaction. So this is kind... Sorry? Yeah, so it's, the question is, are we observing here something like we observed in the hybrid simulation where basically the connection was injecting energy directly at scales comparable with the ion inertial scales? In this case here, we are just going from the big, let's say, ion vortices down to electron scales. They are of the order of the electron scales, but then you can imagine that when you have all these linear interactions here, you will probably go even below electron scales. So I don't know. So we have quite a good resolution because KDE is here, K rho E is here, so we could actually go and look more at this. Yeah, this is the full kinetic simulations. Otherwise, it wouldn't make sense. Yeah. So that's it. So could this be a possible mechanism for, I don't know, for like, so basically through reconnection, we generate these electron beam instabilities, and this could maybe explain at least partially, for example, the perpendicular scattering of the strahl. So what I would like to do is do more analysis on the electron VDFs and possibly also compare with the PSP and solar orbiter data to see if we see these electrostatic waves and this deformation of the VDFs. Thank you.
Quick question. So, of course, the time scales are going very fast now. Are you sure that you don't need like to have you have some relativistic effect at some point? You may need a relativistic peak if this is moving quite fast now, maybe like light.
Yeah, that's something we should actually check. So it's not. No, it's Markidis and Lapenta score. It's IPIC 3D. Yeah, yeah. Yeah. What we checked, of course, is that the initial electron thermal velocity is quite much smaller than the light speed, but we didn't check what the velocity is at this time. So that might be worth checking. Yeah, of course. Yes.
There's a paper by about electron-only reconnection with iPhone and other people, and they pose there that the distinguishing feature is the ability of the protons to turn the corner through the reconnection zone. And I think there's a quantitative figure of merit based on the curvature of the magnetic field lines related to the length of the current sheet.
Yeah.
But I think if you have that ensemble of electron-only reconnection events, you should be able to make a quantitative comparison with their theory.
Yeah, yeah, I think so. I agree. Yeah, that's something worth checking. Yeah.
All right, cool. There are no more questions. Then Giuseppe, please, and thank you very much.
Thank you.
Okay. Yeah, the next talk is by Giuseppe Aro, Energy Transfer in Electric Simulation.
My name is Giuseppe Aro, and I'm a PhD student at day4. Actually, this is my last year. Okay, so my name is Giuseppe Aro, and I am a PhD student at KU11. And today I want to share with you some results I got about turbulence. So as Luca was saying before, turbulence is a really complex problem, as we all know. And one interesting thing is to study the spectral features of for example, in this case, the magnetic field at sub-baryon scales, where we see a fragmentation in the slope of the spectrum, related to the fact that the plasma is a multi-scale system, of course, which means that in different ranges of scales, we have different physical regimes, let's say, and this implies this change of slope in the spectra. And one interesting thing is to actually understand what shape the spectrum takes at these scales, especially when crossing electron scales, where the shape of the spectrum is still under debate. It's not clear if it falls like a power law or exponentially. And also a related problem is to understand what is the physical process behind this steepening and this change of behavior across different scales. So to investigate this problem, I also ran one perfect simulation, let's say, with the let's say, the broader code of IBIC 3D EXIM, which differently from IBIC is energy conserving, but as for the rest is pretty much the same. And the simulation is quite simple. It's a 64 di times 64 di box in 2 dimensions. And everything is constant at the beginning. I choose this beta for ions and electrons to mimic, let's say, magnetosheet-like conditions. Of course, I use a reduced mass ratio, which makes the simulation less perfect, let's say. And the turbulence is triggered by velocity and magnetic perturbations. And both the injection scale and the amplitude of fluctuation are also, let's say, intended to mimic magnetosheet conditions. So this is a magnetosheet-like simulation of turbulence. Okay, so first of all, I started by analyzing the properties of the turbulence at a fixed time when the turbulence is actually fully developed. And as a rule of thumb, the turbulence is fully developed when the root mean square of the current reaches this sort of plateau. So I put myself at this time where the simulation looks like this, and the spectra have this shape. So I won't go into the details here because this is the starting point for what I'm going to show you, but basically I did a fit of the spectra of these three spectra, so magnetic field, electron velocity, and ion velocity, which are related to the three main forms of energy, which are magnetic energy and the fluid energies. And at sub-ion scale, what I find is that both the magnetic field and the electron fluid velocity are well described by this power exp model, which basically is a power law modulated by the exponential. And the important thing is that the exponential behavior starts at electron scales more or less around rho e, both for the magnetic field and the electron fluid velocity. While for the ion fluid velocity, we don't really see an exponential decay. It just falls down like a power law and doesn't reach far into electron scales. So basically, I was saying that this is a starting point because this similarity between the magnetic field and the electron velocity seems to suggest that the electrons are the main, let's say, driver in shaping the magnetic field spectrum at sub-ion scale, which, by the way, it's a spectrum, right? Because the ions are supposed to be demagnetized at these scales. And another hint, sorry, is that if I compare the ratio between the magnetic field spectrum and the electron velocity spectrum, I see this k to the minus 2 scaling, which is consistent with an incompressible electron-driven dynamics, in which case the current is basically all caused by the electrons, and if we neglect density perturbations, we have this scaling for the two spectra, and this is actually what I see. So I see these similarities, but this is, let's say, an analysis at a fixed time, because I'm taking a time where the turbulence is fully developed. And what I would like to do is to actually follow the evolution in time of this sub-ion range of scales, basically. And in order to do that, I basically took the wave vector where I see this break in the spectrum, so the ion scale spectral break, and I divided my range of scales in two ranges. One, let's say, large scale range above the ion spectral break, and the sub-ion range below the spectral break. Actually do this in using this framework. Basically, I'm low-pass filtering the Vlasov-Maxwell system and calculating the equations for the evolution of the energy. Without going too much into details, basically, as you can see here, the filtering basically removes fluctuation at a scale below a fixed k I'm choosing. In this case, k is the one corresponding to the spectral break, as I said. And I obtain this equation for the energy, which basically are identical to the sorry. will take a couple of minutes. Well, if you have questions about this stuff.
So this ratio is the same as for observation of electric field spectrum, actually, that
Sorry?
Lorentz paper 2017 observing electric field spectrum with difference power 2 minus 2.
The ratio between the electric field and the magnetic field, you mean?
And then here you compare velocity, electron velocity, and so you have this 2K minus 2 difference.
Yeah, I actually compared also the electric field and the magnetic field. If I remember correctly, up to electron scales is scale like k to the power of 2, and then it increases to k to the power of 4. But I think I have the plot here. Eventually I can show you.
But so is it the same, or it is different phenomena, this velocity, electron velocity, and electric spectrum? Is it just
You mean the motivation because...
is it whole term in both cases, or?
Yeah, it should be, because if the electric field comes mainly from the old term, which is what I see, and I have a strong guide field. This is proportional to B0 to the and the current, and if the current is indeed carried by the electrons mainly, I should have the same ratio. Yeah.
Okay.
Any more questions? Please. Okay. Okay, I think I was here, so yeah, I was saying I'm considering this filtered energy equation, which are identical. I mean, their form is identical to the full energy equation. So we have the pressure-strain interaction, the electromagnetic work, but in addition to this, we have these two terms, the pi u and pi b, which describe the flux of energy from large scales to subion scales in this case. And this is for the kinetic energy, and this is for the magnetic energy. But since I wanted to distinguish between large scale and small scales, I also introduced these two high-pass filter, terms, which describe the energy exchanges at subion scales. And basically, they are calculated as the difference between the unfiltered stuff minus the filtered energy conversion channel. So in total, I have six elements, which are the electromagnetic work and pressure-strain interaction at large scales, the same thing for small scales, and these two terms which basically represent the communication between large and small scales. And then I also did the composition for the pressure-strain interaction, but this is trivial, so I'll skip this. Basically, I'm doing this to distinguish between compressible and incompressible dynamics. So when p theta is dominant, I'm compressible. When pi d is dominant, I'm incompressible. Okay, but so I took basically those four quantities I showed you before, and I averaged them over the whole simulation box, and I followed their evolution in time. And basically what I want to study is how the energy flows from the large scales to the small scales. So what I see if I consider the ion energy conversion channels at large scales, so above the spectral break, for the ions I see that the dominant terms are the W and PS, while the fluxes are not really important, as you see. And basically, the ions are overall losing energy because PS is positive, which means that the ions are dissipating. W is negative, which means that the ions are giving energy to the magnetic field. So the ions are losing energy at large scales, and if we look at the PS decomposition, basically it's mostly incompressible. The dynamics is mostly incompressible.
Sorry, just can you remind us what the W term is again?
It's E dot J, the filtered D dot J. If we look at the electrons, the situation is more lively, let's say, and I would like you to interpret this as in terms of sources of energy and sinks. Because if we look at the electrons, the main source of energy, actually the only source of energy, is the W, which is positive, which means that the electrons are taking energy from the magnetic field instead of giving them energy to the magnetic field, unlike the ions. And a large part of this energy is dissipated through this PS interaction, but only at the beginning. And this is a result of, let's say, it's a consequence of how I triggered the turbulence. So at the beginning there is this, let's say, violent dynamics, but then it relaxes. But most of the work after this initial dynamics is done by the pi u term. So the flux from large to small scales, which means that the electrons are taking energy from the magnetic field at large scales, and they're transferring this energy to small scales through this pi u interaction. And also, if we look at the decomposition, we see that we have both compressible and incompressible dynamics, but mostly incompressible after a while. But this is not really important now. And now let's go to the high-pass filter energy channels. So here I'm describing the energy evolution of the system at scales below the spectral break, so sub-ion scales. And if we look at the ions, they don't really do much, because the fluxes pi b and pi u are really fluctuating and not really big, let's say. But both W and PS are positive, which means that the ions are always taking energy from the magnetic field, and they're also dissipating some of this energy. So basically, the only source of energy for the ions at sub-ion scales is the electromagnetic field, and they're draining energy from the electromagnetic field. While the cross-scale flux of energy is not really that important. And for the electrons, we see this instead. So the source of energy at small scales is the flux of energy from large scales, which comes from the magnetic field, as I said before. Now, of this energy that comes from large scales, some of it is dissipated through the PS interaction, but it's not really relevant at the beginning. And most of it goes actually in the W. So the W in this case is negative, which means that the electrons are giving energy to the magnetic field. So we are now starting to see, let's say, the global picture, because the electrons take energy from the magnetic field at large scales, they transfer it to small scales, where they actually give it back to the magnetic field. So unlike the ions, they are actually supporting the development of the magnetic field at sub-ion scales. But W is negative, right? But it becomes positive at a certain point, and this point more or less corresponds to when the JRMS, the plot I showed you at the beginning, becomes flat. So when the turbulence is fully developed. And what happens at this point is that the PS becomes more efficient than the pi u. So dissipation becomes more efficient than the actual flux of energy from large scales. Yeah.
How much do you think all of this is general for a steady state turbulence?
That's
how much depends on the initial condition, on the case,
yeah, yeah.
that you are doing, because this can be completely, I don't know.
Yeah, that's
dependent then.
I think it's quite case dependent, and this, I mean, the point here is that if I were to force turbulence, what would happen? Would they settle to this level, and so would I have the electrons continuing to support the magnetic field cascade,
So
or would
can bring back energy to the...
yeah, or would they settle to this point? No, I mean, it's a question. Would they do this, or would they settle to this point? So where they actually dissipate? I mean, I can't answer that because I don't have the forced simulation. So I'm not claiming that this is general. It's just, I mean, it's more to show that this approach is can give a lot of information about how the energy is actually transferred. So if I were to have forced turbulence, it will be even better. But at this point, I can clearly see, let's say, this transition from this kind of dynamics where the electrons support the development of the subion scale magnetic field dynamics. And then when the turbulence is fully developed and the dissipation becomes stronger than the flux of energy, the electrons basically are at a loss for energy and they have to take it back from the magnetic field. So W becomes positive again. But again, this may be strongly dependent on how the turbulence is developed, because in this case I have freely decaying turbulence. So at a certain point I expect that the energy that I put at the beginning is almost, it's mainly dissipated. So that strong forcing that I put at the beginning is no longer sustained by any, let's say, constant forcing. And most likely that's why I see this transition here.
Isn't it true that some of this kind of startup transient is actually analogous to a scene in MHD where you start with equal partitions, magnetic and flow energy, and then typically you stretch the magnetic field so J dot E is actually increasing the magnetic field. It's like the opposite of energy release, right? I think that's kind of happening up to what, 300 or something?
Yeah, and in fact, from this point on, if I check the residual energy, it kind of stabilizes to a value of, I think it's minus 0.2, so it's in favor of the magnetic field.
So it's just that the startup transient is more complex in plasma than it is in MHD, but it's still there, right?
Yeah, yeah.
And it's really the later part that corresponds to quasi-steady state.
But my point is, without forced turbulence, I can't really say if in a stationary turbulence environment it settles down to this kind of dynamics where the flux is, where the nonlinear flux is stronger than the dissipation, or to the other, let's say, to the other regime.
One of the interesting things about your findings, I think you're getting more detail than the Yang-et-al study did on similar things, but you have much more detail. One of the things is it questions, I think, the existence of a subion cascade in the usual sense, right? Because the pi UU terms are, in some cases, aren't doing very much, right? I mean, so it's not really a cascade because there's a dissipation is turning on. It's complex, really.
Yeah. Yeah, but as I said, I mean, the cascade, I will say, is also strongly influenced by how I trigger the turbulence. So this may be, as he was saying, case dependent. So I see this transition because at a certain point, the initial fluctuations stop to drive the turbulence. The real, I mean, advancement would be to have a forced turbulence simulation, but I'm working on that, so.
I think you expect all of it to be beta dependent, too.
Yeah. Yeah, because beta changes the level of the PS, so it's also beta. And in this case, my beta is quite high, let's say. So that also is something that may influence this behavior. Yeah, and to conclude this, if I look at the PS decomposition, it's mainly pi d, so it's basically incompressible. I only have a small dilatation here. So yeah, it's consistent with the ratio between the magnetic and electrovelocity spectra. And last slide. So if I put together the large scale and small scale picture, I can reconstruct this diagram. So the initial idea was to follow the evolution of the electromagnetic energy from large to small scale. And actually, I mean, we have two possible routes that the magnetic energy can take. So one is the direct transfer. And the direct transfer is actually weak, and I indicate this weakness with the dashed line, because the pi b of both ions and electrons are really small, as I showed, and they also don't have a specific direction. Sometimes they are positive, sometimes they're negative, but most of the energy is transferred to small scale through this indirect, let's say, path. in which the electrons take energy from the magnetic field at large scales, then they bring it to small scales through the pi-u interaction, and give it back to the electromagnetic field. As I said, this happens in the initial phase of the simulation, but actually the initial phase of the simulation is the phase during which the, let's say, the spectrum develops. After that, it basically stays constant because this dissipation here is weak, let's say. It acts on time scale which are much longer than the nonlinear time scale. So I start to see these degrees of overall degrees of energy, but it's really slow. So at this point, the spectra kind of settle down. And yeah, so if you want to have more details on that, you can check the paper on this, which was accepted on ANA. And I think that's all.
Thank you very much. There was already some discussion, maybe while Silvio is coming down. Other questions, Luca?
So do you think the fact that the ions are not really doing much could also be related to the fact that, of course, in full peak we have a reduced mass ratio, plus with a large electron beam.
Sorry, in full peak you have?
We have a reduced mass ratio. And also with large electron beta, the electron radius is far closer to the ion scale, so maybe the electrons are actually stealing the ion role.
I think that it's more related to the ion plasma beta actually, which is really high. So if it's true that the ions decouple because of thermal effects, that may affect their behavior. So yeah, that's also something that may cause this, let's say, small contribution for the ions, from the ions. Sorry.
Okay, great. Let's thank Giuseppe again.
Thank you.
And last talk before the lunch break is by Silvio.
It's about 3D alpha wave packets.
Okay.
Right.
Okay. First of all, thank you to the organizer for letting me present this work. And I also want to thank my collaborators, Thierry Passot, Dimitri Lavedre, and Pierre-Louis Soulem, Laboratoire Lagrange at the Observatory de la Côte d'Azur, and Matt Kunz in Princeton. So today, am I touching something? Today, I will present this recent work on the collisions of 3D alpha and wave packets and what kind of turbulent regimes you can get out of them. So I will give you just a brief motivation. So the idea was to look at this, at the possible role of tearing in the alphanic cascade from a fundamental standpoint. So simplest thing to do is to start from the building blocks of the cascade, so collisions of alpha waves. This has been done in the past in 2D by, for instance, Oreste Pezzi with the hybrid model, and there have been other studies. So my focus was just to try to enable, if it happens, this tearing-mediated range in 3D to see if it's there, because I mean, it wasn't observed. And to do it in an easier way, we decided to also decrease the non-linearities in order to increase the eddy lifetime, this turbulent eddy lifetime. So to make it easier for the tearing to grow on top of turbulent eddies in case they do it. And in order to avoid the other spurious effects from other modes, we want to look at the pure alphanic cascade. We use a reduced model, which is the gyrofluid model that was presented by Emanuele before, used at the MHD scale. So in practice, this is equivalent to reduced MHD. So I will just spoiler a bit what I hope to show you by the end of the talk, because it's almost lunchtime. So I will just show that apparently there is an effect like dynamic alignment where turbulent fluctuations tend to align, that it seems to happen also at weak nonlinearities, not only when nonlinearities are strong, so for a critically balanced cascade. And this facilitate and let this tearing-mediated turbulence emerge. And then we derive some we'll show some scalings we derived to try to explain some of these transition. And it's interesting because when you are weak and you allow the connection to enter the picture, it may even supplant the standard weak to strong transition. So let's just an introduction about what some scalings of alphanic turbulence. So you all know the MHD equations. You just recast them in the Arcetri formulation. Here I take viscosity and resistivity the same for short. And you have these Z plus and Z minus, which are Alphen wave traveling up and down the magnetic field. And then you have the nonlinear term, which is just the interaction of counter-propagating Alphen waves. So this is the basic idea of why we look at the alphanic turbulence from the building blocks, the interaction of counter-propagating alpha wave. Just to introduce some notation, imagine you linearize this equation, not linearize, but you split the background and fluctuations, and then you get two terms, which will be used later to define the regimes we are studying. So one is the linear frequency, so the linear time scale, which is the Alphen wave propagation time, and the nonlinear frequency or nonlinear time scale associated to it. And I will use this parameter chi, which is the ratio between these two time scales, which is the nonlinear parameter. So when a nonlinear parameter is small, it means you are in the weak regime, so nonlinearities are weak compared to the linear time scales, whereas when it's order 1, you are in the strong or critical. Huh? That's a good question, and I think it won't stay much longer to that, because to that regime. The idea is that if you try to steer too fast, I mean, the point is that what happens when it's much larger than 1? You are decreasing the nonlinear time scale. So you are basically decorrelating very quickly the turbulent eddies in the perpendicular plane, and there is only a finite length that can be traveled along the field line to keep the causality, right? So I don't think larger than 1 will really stay. I mean, order 1 means maybe 2, 3, but like 100, I don't think it's.
In a paper by Sean Outland and myself 2 years ago, we completely debunked that argument.
It's, yeah, I'm not sure. Yeah, but I'm not sure if it's gonna stay. We didn't try, so it may. Yeah, but in 3D. I mean, in 3D.
No, but the two-dimensional part of the 3D spectrum has infinite chi, and that's the most populated and most turbulent part of the spectrum.
The KE parallel equals 0. Yeah, it's a structure. So it's a. Yes, it's structured. Yeah, but then does it make sense to talk about a linear propagation time?
People who say that can't be bigger than 1 are critical balance people who want to throw away the non-propagating structures.
Yeah, no, but that's the point, because they're not propagating. So does it make sense to talk about a linear propagation time? It's an advection maybe time, but maybe. Yeah. But then what is K parallel VA for them? It's not clear. No, but I agree. There are structures, and we'll see there are structures, but they're not in this regime because K parallel is not. I mean, when K parallel goes to 0, is that you're not in the. Huh? No, yes. So we would like to look at that, but. Yeah, exactly. Exactly. That's the point. So the wave packet will have a finite K parallel. So, but I agree that structures are not in this ordering in this sense. And then it's useful to. So the cascade time will be related to the nonlinear parameter and the nonlinear time scale. So only when chi is order 1, they match. The cascade time is the nonlinear time scale. So this was just a classical phenomenological picture of what happens when you inject some energy in a weak regime. It will first cascade towards smaller perpendicular scales without keeping K parallel constant with a certain power law in K perp, which is K perp to the -2. But then if you look at the nonlinear parameter, this will increase, and so what it will happen is that an initially weak cascade won't stay weak. At a certain point, it will reach chi order 1, and then we'll potentially go to a critically balanced cascade. Without. Okay. But we observe that. So, another thing is that if you make a further step, Boulder was suggesting that there is this effect called dynamic alignment, where you have alignment of velocity and magnetic field fluctuations, and this modified the cascade time. So your spectrum is supposed to be -3/2 instead of -5/3, as in a critically balanced case. And also the anisotropy is different. So this might be a diagnostic to see whether it's more Golder-Schroeder or Boldyrev-like, so aligned. But the one important thing is that if you believe this is what is happening, what is important is that you are building up a three-dimensional anisotropy in the turbulent eddies, and then therefore you can look at the perpendicular plane. You have anisotropy in this plane. You have shear elongated eddies which resemble a current sheet, and so the idea at a certain point was, well, if these eddies live long enough to allow, and they are in a configuration which is steering stable, and steering may.
So these are eddies which are elongated.
Yes, this is just the cartoon. It can be also two eddies which are in contact, as we well know. But this is, this is just.
This is coming from the dynamical alignment.
Yes, exactly. It's not the same.
There's a strong alphanicity there.
Yeah.
Instead of the vortex where the alphanicity is close to zero.
The alphanicity is.
Cross-edicity near the point where the vortex interact typically is very low.
Yeah. Yeah, no, this is, there is, I mean, if you align fluctuations as scale dependently, then your cross-helicity and residual energy is scale dependent. But yeah, what you're talking about is large scale and the edges. Don't agree. And so, well, the point was, so if this can happen, let's see how the cascade becomes, the range becomes. If you have a new range, which is the reconnection-mediated range, and then there were a few people deriving these scalings for the tearing-mediated turbulence, which changes the characteristic of the cascade, the spectrum, and the alignment, and the anisotropy.
But then, if you have this reconnection, as Bill was saying, you might have some structures that stay there and approach.
But in fact, this is.
So it is omega zero.
No, exactly, but in fact, when I discuss this in the paper, I say that this must be strong in the sense that cannot be, even if you arrive there, which are weak, and you trigger this cascade structure, so it has to be strong. I mean, strong in the sense if you try to define a parameter to measure the strength.
Strong in your sense, not in the sense of omega zero. You're always in the framework of strong means critical balance.
Well, it may be critical balance, it may be much larger than one. Just say that it has to be a strong, at least critical balance, critically balanced, at least. But that has to be measured. I mean, it's not clear. This is totally unexplored at the moment. So yeah, I agree. So this was the picture. And then the question is that, but do you see this in simulations? It's like, well, do you believe it, and do you see this in simulations? There were some work by Chuanfei Dong and the collaborators in 2D that were trying to show this, but the problem with a full MHD simulation that you need a huge resolution that was done only in 2D up until a few months ago. I discovered that Dong had done these 3D huge simulations where they see this limited range of -11/5, but they had to use an insane amount of CPU hours. Now, 200 million CPU hours, I really don't have it, and so I wanted to do something simpler since the beginning, and the idea was to do the simple setup and to use some tricks maybe. So as I said, what can I do? So if I want to meet this condition, where the reconnection timescale meets more or less the nonlinear timescale or the cascade timescale, is that either you can try to enlarge this range, so have a larger range by increasing the Lundquist number and separating more and more the transition scale and the actual dissipation scale, or
I don't understand the philosophy of this kind of approach. I mean, the nonlinear time occurs because of the sum of all the nonlinear processes that are present in the turbines. The reconnection is one nonlinear process within the turbines, and you want to separate it out. And
you want that this becomes at least as fast as all the other processes, right? So when it becomes faster, then it will.
There's just a question, the nonlinear time at which scale?
Yeah, no, this is scale dependent. No, it's this is I didn't put it explicitly, but it's a function of k. So this gives you more or less the scale at which you expect to. So this is the idea. You can write it as scale independent, but if you want to find the breaking scale, you need to look at the scale dependence of the reconnection rate and the yeah.
I did something similar, not really similar, but when I was plotting
Yeah, exactly. It's comparing the reconnection.
I read contours saying when the average reconnection rate was matching the nonlinear time, so it was equal to 1. So it was changing, of course, with time.
Yes.
Statistically stationary scale.
Exactly. And that gives you more or less the break. Should give you the breaking scale if you know exactly how the reconnection rate depends on k and your cascade time.
Well, the reconnection.
Yeah. So now the idea is to facilitate the emergence of this range by increasing the lifetime of the eddy, so lowering the nonlinearities. To do this, as I said, just throw two Alphen waves at each other. I use the Hamiltonian two-field pure-field model, and I use a combination of resistivity and higher order resistivity to cut off the final part of the spectrum. And yeah, pretty much that. Don't go into the details here. I have backup slides, exactly, because I don't think I'm going to make it. Well, we reach, if you normalize to the turbulent peak activity time, we reach peak activity, and then when I'm not saying it specifically, I'm averaging the results around this peak activity. Yeah, just to say that when nonlinearities are lower, you need a large amount of collisions, but not as large as you would expect from classical weak turbulence scaling. Maybe because at a certain point you start reconnecting and you just develop the rest of the cascade. So this is just a plot of perpendicular magnetic field fluctuations in two planes. So one is a plane that contains the mean field, so you see the packets highly distorted at chi order 1, and the perpendicular plane you see the turbulent fluctuations with no clear structures in the sense of magnetic island, if you want, or ropes, if you want. And the inset is just the z average along the magnetic field version of this large plot. Then you lower the nonlinearities and you start to see something. This is after the peak activity, so 1.3 in units of peak activity time. So it's slightly later where turbulence is developed. Now you further lower the nonlinearities and you start to see that you have generated some structure in the perpendicular plane. Especially, you don't have distorted much the. This is this is a plane in the perpendicular plane, a slice, and this is the average version along B naught. Yeah, they travel along the magnetic field. They just. Yes, they have an envelope. It's a packet. These are they've been collided more than 100 times in this plot. Here, maybe 20, 30. I don't remember exactly. Here, just I think just not 8 or 9 times.
Sorry, so did you say that the big picture on the right is the average in the parallel direction?
The small picture, the
small one is the average.
yeah, yes, the small, the inset of the.
But it's brighter. I shouldn't. Does that mean
No, I just put. This is not the same color scale of this.
it's not the same?
Yeah.
But that means that there are non-propagating structures.
There are.
Which by themselves have infinite.
Well, if they're weak, I don't see them very well when I try to follow them in the time. So I'm not sure whether they're propagating or not. Or, I mean, transport by. But what I see, I will show you a video now. If I probably I don't. Yes, and exactly that's the control parameter of these different regimes. So this is chi.1. I didn't say it, but sorry. It's, from chi1, I lower the nonlinearities, chi.5, and to chi.1, so very weak nonlinearities. Well, yes, but this was simple to diagnose. Yes, I wanted to start from a simple setup and then maybe go to very. So I will skip the movie, just showing that this minus 11/5 range seems to emerge. There are some larger scale range which I try to explain, but they're very limited. They are not meaningful in these simulations. The important thing is that alignment is happening, and is actually very patchy in time. So for a simulation where you inject a broad range, it may be also very patchy in space. So it's important to understand how to actually measure these quantities. If you average over the entire box or over time, in this case, you see something which is not clearly, I mean, is something, but it doesn't correspond to anything that you expect. Just because it is a complex convolution of different processes occurring, maybe in this case periodically, because we are triggering these things periodically. But you have like -1/4 as predictable boulder for the chi order 1, and you have slightly different power laws. And when the packets are far away, so this is when they're in country or just encountered, so they shear each other, so they align them, they align in a scale-dependent way, whereas when they're far away, so you have this trigger cascade of magnetic reconnection, you have the 4/5 as predicted by the theory-mediated range, for the theory-mediated range. Just mentioning that you can play, assuming that there is alignment in the weak regime, and try to derive some scalings, which seems interesting because in one case, if it's not so weak, you recover also the -3 halves. It's just the alignment angle that scales differently in this case. So you can, if you see a 3 halves, maybe you are still weak, not really strong, but the angle will scale differently, for instance. So and the other case is a symptotically weak regime. You find a quasi 2D regime where you have -1 spectrum for the magnetic field and a very strong alignment. Now, I wanted just to tease you with the fact that actually the alignment in the 1/f range has been observed, and I think only here. I don't know if anybody looked at this anymore. By Weeks in 2013, they found alignment or anti-alignment of both Z plus and Z minus and B and B. I mean, you can look at two things, and the two things may scale differently, actually, the angles between the two things. And another thing is just really teasing. Is like, this is when Parker's solar probe entered the magnetically dominated corona. Is this minus 2.2-ish some sort of reconnection because it's above ion scales? I don't think it's necessarily the elicited barrier, because then in that case, you would expect a flattening of the spectrum to the minus 2.8, and you will expect a very steeper transition, like -4 was shown before, and that's pretty much it. Just saying that there are more things to do, look at, possibly play with, like here I didn't talk about imbalance because the simulations and the phenomenological scaling I was deriving just balance case. But it's important to look at imbalance case if you want to actually understand the solar wind. And I was just like, would be nice if someone else look at these features in the solar wind in the 1/f range, if there is alignment, and a way to evaluate find a way to evaluate the strength of the nonlinearities. So thank you, and sorry for being.
You already spoke about tagliatelle and lasagna on your slides.
Yes.
That was me.
Exactly. Yeah, exactly.
Any other questions for Sylvia? There was already some discussion during the talk. Over lunch? More discussions over lunch? All right. Then
No, I want to
let's thank
discuss with
Sylvia and all the speakers of.
I wish you put your new email address. If nobody has.
That's true. I forgot to do that.
You give me your email address, I would appreciate it. Does it still work?
It still works, but I don't know for how long. tonight?
No, I actually think, I was making the list, I'm pretty sure that we have a position left.
Okay, my problem is that I'm coming with 3 people.
Who are the 3? Oh, I don't know if I have 3.
Sorry?
I don't know if this, we have.
Myself, my daughter, and her partner.
Ah.
So if not, then we. Okay.
Yeah, I have to.
Place.
Okay, the answer is, let me check.
I don't want to disturb you, you know.
We would like you to come, it would be nice if Stuart would be able to hear too.
Yeah, you know.
But,
my daughter is with me.
you know, we're going to this restaurant, I know you like it.
La Casalinga.
So it's hard to get in.
I
And
know.
I booked, I took a chance and booked 12 places.
Okay.
And I got it, which is not so easy.
You want me to call them? Or you speak Italian?
No, but you're better than I am, of course.
I can negotiate well.
But I'm not sure if we have the 12 filled yet.
Okay, I let you, just let me know whenever you want, or I can call them.
I have to ask people.
Okay.
Here, I'm gonna full disclosure, okay, full disclosure. Here's my, I meant to ask you yesterday, but
I was not
here's, this is my core memory, I'm trying to remember.
Okay.
I know we have Denise and Alessandro, me and Colleen, Kuili and Olivia. Then I'm pretty sure Sergio's coming, I'm pretty sure Chicho Pecker's coming, although he's such a nice guy, he would drop out to help if we want old guys to come.
No, I don't.
I'm Charlie, you can't throw Charlie out,
Okay.
I'll be in trouble for the rest of my life, and I'm Oka's coming.
Okay.
So if everybody there, that's 1, 2, 3, 4, 5, 6, 7, that's 10,
Okay.
okay?
We have 3.
Okay, and I don't know if there's anybody else that I'm forgetting, I have to ask
You know,
Denise.
Okay. But you know what?
If Denise says this is really it, then I can tell teacher like, you know.
No.
And then we would have 3 slots.
No, I mean, it's okay. I mean, we can even sit
Or you can
nearby.
try to get a table nearby,
I can have a table nearby. I can call them.
and then I can come over and you and I can get drunk and.
I don't know if I will get drunk. I was sick yesterday.
Okay, I hope you feel better.
I feel better now.
Are you talking this afternoon?
No, I already talked.
You already talked?
Yes.
Oh, that's right, the minimum.
The baseline solar wind
Baseline
that you
solar
don't
wind.
like, but
No, just the questions, you know.
of course I will write the paper and you can argue.
That's why we write papers, is to have people question them, right? Okay, let me check with Denise.
Okay.
Monsieur Milan.
Yes.
I already remembered one that I had forgotten, and that's
Okay.
more.
Okay, of course.
So already, so why don't,
I will call them.
why don't you call them
And
and
I
ask
say
if you can get a table for
for
3
3 nearby.
near the big table. Talk to Andrea if you can.
Andrea over there.
Yeah. He usually helps us.
Okay.
Tell him that you know Bill.
Okay.
He may not remember my name.
I will arrange that.
think. So you're okay. Yeah. So you okay? I'm just setting my computer up now. Because my battery is sure. It's going to take a while. I have to. But you can leave my computer here. Sure. So they only have this. So you have it here.
Anch'io le cose.
Hope it doesn't flicker again. It might be something to smash. You need to test anything?
I don't think so. I looked on the HDMI straight and it never failed.
Okay, good.
There is HDMI.
Yeah, I thought since your computer was printing the first time, we should have left it set up. Now it's working, but you're okay.
Now it's not. It got switched.
I think. Hello? It's working. Okay, let's reconvene. So I'll be chairing this afternoon. So next talk is by Lee.
Yes, you got it right.
And the title is already on the projected, so I'll give you kind of a bit of warning, but you understood the spirit of the meeting.
Yes, yeah.
Okay.
Thank you. This is my second time in this meeting, this series of meetings. We enjoyed all the discussion. So this is work on compressible MHD turbulence, that a topic we've been doing recently. The two postdocs who did most of the simulation, I worked with them on some of the analysis. We have several papers. Two of them are already appearing in FJ, and there's a third one we're writing right now. Okay, and so given the time, I mostly want to focus on one issue. This is low frequency. We call it non-waves, but I guess this community calls structures or 2D plus slab in compressible MHD. I want to. So I come from the astrophysics background. In case you didn't know, we were carefully taught another worldview. But I've been interacting with Bill since '96, so he has been also teaching me the space physics view. So this is part of the purpose for me to come to this type of meeting to understand different perspectives and how to integrate them. And I mostly want to present some of the 4D FFT analysis of the fluctuations. This is an approach that was also done by many groups around the world to look at MHD turbulence using that type of analysis. And I want to discuss mostly what we consider the origin of the low frequency phenomena, and then summarize. So very quickly, I'm assuming all of you are familiar with all this, is that the linearized MHD eigenmodes have affine, slow, and fast, and their dispersion relations. And if you plot them in omega versus k vector plane, you can identify discrete modes. And this is actually a 3D MHD simulation with different waves, and just wanted to make sure our codes work. And just to refresh our memory, in this plane, omega versus k, the affine and slow modes are two sheets, and the fast modes is actually a curved space. So there's kind of well-known work in the space in the ASTRO community by Cho and Lazarian back in 2003, and then there's a bunch of papers. What they did is they run compressible MHD simulation, turbulence, and in real space, and they Fourier transform into K space, and then they proposed the mode decomposition based on the spatial polarization information. So you can write down the polarization vectors, and that's a unique set of orthogonal vectors that eventually you can decompose all fluctuations into three type of polarization modes, which they call affine, fast, and slow. And then they quantify how much fluctuation resides in any of the three, and also their spatial properties. And this is a summary of a recent careful work by Makawana and Yan in PRX, I believe. So what they did, they carried out a set of simulations, and then they used the mode decomposition that I discussed in the last slide. And what they found was what they call affine, slow, and fast. There are different types of driving, and they typically arrived at the conclusion that the affine modes is about 20–30%, and depending on the driving condition, beta, you do sometimes get fast modes and slow modes as well. Now, this type of analysis is of great interest in many communities because we want to understand cosmic ray particle transport. We want to understand particle acceleration, accretion disk around the black holes and AGN jets, and so on, whether you can decompose fluctuations or turbulence in terms of those wave modes, and whether you can then go on use
for example, gyro resonance conditions. I think some of the talks on Tuesday were kind of went along that line, although others might disagree. So there's still key question remains whether you can actually do this kind of decomposition. And even in some of the space communities, many of the groups are still continuing to use this approach. So what we did here is, in addition to the more traditional spatial decomposition, and imagine you can also save lots of the 3D frames with high time cadence, and they can do the temporal frequency information. And this is the plot I showed earlier.
Well, you can just make a quick comment.
Yeah.
Just that decomposition, if you look at that on the left, it says that the Alfvén mode is perpendicular to the magnetic field, right?
Did I make a...
No, you're right. I mean,
oh,
you right,
oh,
you
okay.
But I mean, in this community, we're used to looking at constant magnitude Alfvén waves that, you know...
The Alfvén waves, yeah.
Spherical polarization. So
yeah.
That rules out the spherical polarization.
Yeah, there are... Yes, there are... That's actually, I didn't realize that point because we did the parametric decay instability study. For example, we used arc polarized Alfvén wave. That you're saying those waves would not satisfy, yeah. 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 So, good point. Anyhow, so let me skip this slide. So we tried many different runs, like we listed a few here, whether you can drive velocity alone or you drive both velocity and B field, whether the compressible driving, this is incompressible driving or the highly compressible driving, and different correlation functions, different plasma beta, and different turbulent Mach number, and so on, different resolutions. And so where we're heading is trying to do 4D omega versus k plots like this. Indeed, for some of the special runs, we can see that we can.
Sorry, this k parallel means that you have is along the mean field.
The mean, yeah, the mean initial field, yeah.
Mean is along z, for example.
It's actually x, but yeah. We didn't do the local ones. Yeah. So I mean, this is, you can see sometimes you can separate out those modes through this approach. So this is kind of typically what we get. This is a busy plot. So this is omega axis, and you can see the driving effect that you get a lot of power over here. The color indicate power. Apologize for the small font. This is 10 to the 9. This is 10 to the 1. So you have a huge range here. And you can see immediately that you have most of the power at a very low frequency, populating K perp from 0 to some large number. So is K parallel from 0 to large number. But nonetheless, they're nearly zero frequency, very low, but nonetheless they're resolved. They lie down over here. There are arguably some modes that went along the dispersion planes. So if you do cuts of those planes, you can kind of see that indeed as a function of K parallel, and you get the slow mode, Alfvén mode, that will be the fast mode over there. So this is as a function of K perp. This is one of the things that you can see. This is the driving, and this is the Alfvén modes. And then you have this huge amount of power that does not fall on any of the dispersion plots, regions. So you can do the similar quantification that we kind of have tried different ways. We do the incompressible driving, compressible driving, incompressible with VMB and compressible driving. And then when doing the the counting of the different modes, we also tried three different things. One is we do the traditional, the left bar is the traditional spatial only decomposition. And then the middle bar is spatial only, but we exclude the driving region. Turns out that's the dominant power, right? And the right bar is the spatial and temporal quantification that we only take the ones that's on the dispersion plane plus some width. We call those are thin, fast, and slow. And then for those do not fall under on any of those dispersion planes, we call it non-wave. So that's those gray bars here. So you can see that once you exclude the driving region and do the 4D FFT quantification, predominantly you get the non-wave, up to 60, 70%. In retrospect, this is actually something that's known in the community by many groups. Even myself, we did some studies in kinetic simulation. We found this patch. And this is work by Jason Tenbarge and Greg House. They made omega versus K perp in their gyrokinetic study, and they found a huge amount of low frequency power. And this is a paper by Moran and French group. They also, this is a PRL, when they did the weak to strong turbulent transition, they had this huge amount of power in omega versus K perp. This is work by Andres and Bill and others. They also found a huge amount of power, and there's kind of a hint of waves. And then another former collaborator and I wrote some papers, and we also found something similar in those. And if you go into some of the early work by this is what, 15 years ago, 2007, 2009, you all recognize this guy. And so they made plots like this, right? So this is frequency times power of frequency in energy units versus frequency. Their paper was focusing on maybe this is summing up all K. You just do a total power versus frequency. They were focusing on maybe this region is more like 1 over F, and you see this interesting peak, and then it rolls over in log space. And then they also did this interesting plot where they go into the simulation and say, what if we choose a particular K, Kx, Ky, and Kz, and they get this shape. For those who still remember, maybe not high school, but undergrad, those shapes look like what? No? Okay. So, I mean, they did, so I don't know whether they probably realized later on, but in the paper you search the word Lorentzian, it doesn't appear. But those shapes looks like Lorentzian, okay. Right, so you have a peak, and you have very broad wings. Okay, and this is power versus omega again. And so what their work is saying that you do your compressive MHD simulation, you don't do, you look at the time domain behavior. Total power kind of did this with some structures. There's parameter dependent. They try different betas, different mean fields, and if you pick out a particular mode, again look at the frequency behavior. There is a peak, and then there are very broad wings. So what we did was, going back to everybody solves almost the same equation, right? So we look at this equation and say, what if we drop this term, just evolve this funny equation? You don't get any of those low frequency features, and this is when you keep everything and decompose, we have shown earlier. So if you go back to look at this equation, and many of the speakers already talked about, this is the compressible MHD. And if you then move everything to the left, you write equations this way and move this guy to the right, and you think of a damped oscillator or driven oscillator, depending on which way you look at it. And if you remember the MHD, you drop the nonlinear term, you get eigen wave reaction. So that's the peak. Indeed, you're going to see the Arfin frequency, the fast mode frequency, and slow mode frequency depend on K. But because of this nonlinear term, it acts like the broadening as well as the big wings. That's the damped oscillator equation. So you can expect the frequency behavior of this equation more or less follows this shape. How am I doing on time?
You have soon it will be 5 minutes to go.
I'm 20 minutes, 5 minutes to my 20 minute?
15 minutes from the beginning.
Oh, so I should, okay. Anyhow, so, again, doing something similar to what I showed, what Bill and others did earlier, you pick out different Ks, you get this kind of behavior and with a peak around either for Arfin modes. So we now do it for 3 different modes, Arfin, fast, and slow. And then you can actually write omega in terms of the eigenfrequency plus this omega nonlinear. I think the speaker before lunch also had that expression. And you indeed expect this kind of Lorentzian behavior. And now you can fit it for different different wave modes, where Arfin, again, using the spatial decomposition for Arfin slow and fast. You can see it, they peak for this beta, which is high beta, then the Arfin is slow are same peak, and then the fast is over here. And then you can try to fit them differently. And for low beta, and then you can now separate slow, Arfin and fast, and they peak at different frequency and then always with different wings. So the fact that you have so much power at low frequency, that we think is the origin as to why when we do the 40 FFT and the summation, it's almost a 1/f behavior. And let me just try to wrap it up. And this is a recent paper I found online. This is by Zhao et al., Huirong's group, where they use MMS data in the solar wind. They're trying to pull out such spatial information. We think by doing the Lorentzian time analysis, it should be able to demonstrate that as well. So to summarize, I think the production low frequency fluctuation is actually decaying eddies, right? So you have a damped oscillator, you do a Fourier transform of the time domain, you're going to get this Lorentzian behavior with loss of power in the low frequency. And this suggests, okay, there's some future work. I think now, if we think we kind of have a general framework as to what generates low frequency and overall, and we can still go back and then look at Arfin slow and fast modes in low beta, and to figuring out whether different modes would have a different scaling in K-space, and as well as their cascade rates, how would that be different? Because now we don't separate it as, dare I say, 2D plus slab. There's still a mixture of wave modes, but each mode covering a broad frequency range. And then we expect for different betas and scalings will be in K parallel and K per will be different. And of course, I still want to understand how this kind of more single framework with the very broadened frequency response, how that relate to the more typical 2D plus slab picture that space community has been using. Thank you. Yeah, so for those who are still tracking with what we're talking about, for some reason, even though we use Lorentzians to kind of fit every modes we get, you sum up all the power here, and you get something like this. So, sorry, there's like 4 different runs where we try different betas and different sonic Mach number. They kind of varies somewhat, but this is just to get your eye is 1 over f. So
How would you explain then that disappears completely when you don't have an inverse cascade?
yeah, so I mean, a naive way of thinking of this is in a quasi-steady driven dissipative system. I would argue, like y'all empirically, you show this as well, right? So you integrate over the underneath the area, you get a constant, which is what you would expect, right? So, if this is different from 1 over f, I think we'll have a trouble. It is 3D. We have some amount of helicity, but not maximal. So that I don't know the short answer is I don't know why it's 1 over f yet. Yeah.
And the other thing is that the wings on the Lorentzian are all lower than the peak at the resonance. And they are symmetric. And they're symmetric.
Yeah, but
if you look at the high K modes in the Dimitrov paper, there's no peak at the resonance at all. I mean, so.
yeah, so the total amount of power within the peak is a small percentage of the wings. I mean, depending on how you define the wings, but I think even in some of your papers, you point out that's, well, it varies as a function of mean field, but its range can be as small as less than 1%. Yeah. Yeah.
Yes. So, you say your turbulence is forced. What about if you will be a decaying turbulence? Will you still see this program direction?
The Lorentzian profile stays, then the decay is 1 over omega squared.
No, but if you don't force the turbulence.
Yeah. So we do decaying turbulence. Yeah. Sorry, the power versus frequency is 1 over omega squared, but we still get the Lorentzian. Yes, if you choose a particular k parallel k perp and do the frequency power. Yeah. So the Lorentzian is intrinsic because of the damped oscillator. Yeah, picture, yeah.
Okay, Sergio, last question. So what if you drive it slow, with very low frequency, which is very physical probably for the solar wave? I mean, you are driving with some given frequency here, right? You're driving as a characteristic.
We're injecting a small k, which is maybe frequency. Yeah, we didn't change the frequency part. We may change a little bit in terms of the correlation time.
We did it once, and if you lower it a little bit, all of this disappears. If you go to reasonable, like the photospheric motions or very low frequency thing, then all these branches really disappear. That's
What disappears?
all this resonance slide that you observe. If you lower a little bit more your frequency of driving, then you can see an effect on this special relation you were showing.
I should get to know more about that. Yeah.
Okay. What are frequencies normalized to here? What does 1 mean for frequency?
The Arfin frequency. Yeah. So using the. Yeah. We can't. I'm not relating it to solar wind. We're just saying in a yeah. Yeah.
Occurs like 2 or 3 decades to the left of what you're calling 10 to the 0. So you're like in the middle of the eigenmodes where you're getting this buildup.
Yeah. Well, we go to about 100 Arfin time. So.
You should go to 10 to the minus 2.
You're
only going to 10 to the 1.
Oh, maybe we go so that in order to save the frames to do the Fourier transform, we go to 100 Arfin time. Maybe I misremember the normalization here. Yeah. Yeah.
Okay, so next talk is by Martin Laming, the inverse FIP effect in the solar and stellar corona.
Can I say something?
So
You want to suggest a group picture?
Yes, before they leave. Yes.
Yeah.
So should we take it now before we go?
But we will do it well.
Here. Yeah, I guess. Here. Yes. Okay, yeah.
guess sit near the middle.
Everybody is here. No, I will not be in the corner. Please go to the. Sit down, everybody sit down. Sit down. Huh? It's not enough open. My camera is not enough open.
I have everybody fixed. Okay, good.
No, I'm not here.
Bill, what about you? Can we get someone from?
No, you have to come in. But how can
Is there someone in the office?
Get somebody to.
Is someone in the office we could?
I'll take a couple here. I hope Simone's taking one. Smile. One photo. Let's see if there's somebody. Maybe I can ask the caterer to come. Okay, here we go.
Milano.
Behave yourself, Milan.
I want to make a photo with you.
Okay.
You go there, I will take a photo.
Yes.
Okay.
Okay, perfect. 1, 2, 3.
One single.
Okay. Voilà. Voilà. Another one with this one. That is. Okay. Can I make? Ah, yes. Voilà. Attention. Huge sail. Voilà.
And can you also use my camera, please?
I cannot change your camera, okay?
No, no.
I need to make 2 and then you can play. Voilà. And another one. Voilà.
Merci,
You were very persuasive. You told them you would spoke in Italian. 15. Right where you were.
Sorry.
Ciao ragazzi.
You can say goodbye to the Calabresi and then you should go. Bye Calabresi. Bye Calabresi. Too many kissing. Too many kissing here. Okay. Let's move on.
Okay.
I'll let you know when you're on board, okay?
Yeah, okay. I'm Martin Lowing from the Naval Research Laboratory. Since we're in Florence, I thought I'd start off with a bit of art. This is the Naval Research Laboratory here, viewed from the Virginia side of the Potomac River, as it looked in about 1992 or 1993. Now on to the science. I'm going to talk about what has become known as the FIP effect, the first ionization potential effect. First seen, and I think we can say he saw it, by Stuart Potash in 1963 in a paper published a couple of months before I was born. What he saw, and this is a modern view here with black dots taken from Donald Reams, elements in the solar corona, in the solar energetic particles, and also in the ejector of coronal mass ejections, elements with a first ionization potential below about 10 electron volts. Here, so we have potassium, sodium, chromium, iron, nickel. They are enhanced in abundance by a factor of about 3. The number varies from place to place, but there is a sort of a uniform enhancement of abundance here, and then it drops down, and the high FIP elements are relatively unaffected. What I'm showing you here are black dots. The green short dash or magenta long dash curves are models based on Alfvén waves. The green are torsional Alfvén waves, the magenta are shear Alfvén waves, and these are, as I'm going to explain in this talk, comes about as the ponderomotive force. You're meant to be impressed by the fact that these two models actually capture the effect very well. For essentially one free parameter that matters, that is the amplitude of the wave. The important point here is that this has been done for a closed loop where the waves are bouncing backwards and forwards. The waves are in resonance with the loop. And that gives you this pattern. The fact waves being in resonance with the loop sort of implies that the waves are generated in the loop itself. That's how they become in resonance. And this will be a nanoflare type excitation mechanism. And there is now evidence for nanojets in loops. Here is something from a recent paper by Ramana Sukumaji and co-authors. So this is coming about because we have resonant waves probably excited in the loop. The bottom panel shows the FIP effect, the abundance anomaly, also from Don Reams. This is accelerated particles in co-rotating interaction regions or in the slow-speed solar wind. We have something rather similar. We have an abundance enhancement of low FIP elements of about the same magnitude. But notice here, sulfur, phosphorus, and carbon are being enhanced here, whereas they are not enhanced here. This is a significant difference that I think as people are beginning to appreciate. And this implies that this plasma cannot be part of the slow-speed solar wind, which is something Noor was talking about a couple of days ago. You're meant to be even more impressed now that a model based on an open field with waves traveling upwards and down captures this effect. The same model atmosphere is only the way the waves rearrange themselves in response to the magnetic geometry that gives you this change. So I think this is an important development. Just for completeness, I'll show you a model for the fast solar wind. Now here I've taken a wave amplitude from one of Steve Cranmer's papers, observed with UVCS, and here we got the torsional and shear waves. The shear waves do a better job. You have a lower abundance enhancement now because here the magnetic field is about 10 Gauss, so the plasma beta equal 1 layer is at about 1,000 kilometers altitude, so you're only fractionating in the top 1,000 kilometers of the chromosphere, whereas previously the magnetic field was about 100 Gauss, 150 Gauss, so you have much more depth of chromosphere in which to fractionate. The amplitude of the wave, let me... okay, no. The amplitude of the wave here is about 100 kilometers per second. Well, let's say 50 to 100 kilometers per second in the corona. The important number is about 10 kilometers per second in the chromosphere. Here, in the fast wind, at about half a solar radius up, it's about 300 kilometers per second. And you just extrapolate that back by non-WKB Alfvén wave transport, and you get the right abundances. Okay, so...
sorry, and of course, an important assumption that for clarify is that the fractional abundance doesn't vary
beyond
a given point.
Yes, and they may still vary, but by small amounts, I think. And I'm not really going to talk about that. That's too much for 20 minutes. I'm going to talk about the basic fractionation in the chromosphere, which is the dominant fractionation we see. So all of this is due to the action of the ponderomotive force in the chromosphere. So I'm going to spend a little bit of time explaining to you what the ponderomotive force, what it is not. I hope I'm not insulting anybody by being more pedagogic, but in my experience, very few people really have a proper understanding of what we're talking about. So the simple explanation of the ponderomotive force. Here is a famous cartoon, famous album cover from the 1970s. My question to you, as light refracts through the prism, which way does the prism move? The answer is it moves upwards. If you're conserving energy momentum between the light and the prism, if the light is going downwards, the prism must go upwards. This is what is happening in the solar chromosphere. The MHD wave behaves the same way. It sees the ions, but not the neutrals. So you see ions moving in response to the wave and the neutrals being left behind. This is the important phenomenon. So it's basically refraction. We can be a bit more, I believe I'm right in saying that this type of mechanism is new to solar physics and astrophysics. Someone correct me if I'm wrong, but it is not new to science. This has been thought of before. Nothing is new under the sun. In fact, the analog of this in optical light has been exploited for the laser trapping of atoms, molecules, ions, biological samples, and it won Nobel Prizes for Stephen Chu and Arthur Ashkin. Those of you who know me will probably know I did my PhD in atomic physics, and I was in a department where lots of these sorts of experiments were being done, but I didn't realize the connection between this model of the Fipp effect and this work until I read about Arthur Ashkin's Nobel Prize in 2018. I must have sat through many seminars on this, and it just went in one ear and out the other, completely, slept through it all. So, so consciously at least, I didn't realize the connection. And I was a little bit embarrassed when I realized that I should have thought of this a long time ago. So, another way of understanding the ponderomotive force, I'm giving you the expression for it up here. This is the fundamental expression for it, for Alfvén waves. When I first started this work, there were many expressions for the ponderomotive force in the literature that didn't always agree with each other. They must have different ideas of what they were treating. So I went away to derive it myself. Here I got two derivations I found, which are quite complicated. They use lots of properties of Alfvén waves, and they're not really all that illuminating in terms of the physics of what the wave is doing to move stuff around. You do get the right answer reliably, but understanding the physics that's encompassed in the equations is a little bit tricky. Yes.
There's another model, maybe kind of one-to-one with what you're talking about, I remember by Mullen and somebody else, where you orient the reconnection jets upwards, kind of like what Nora's talking about.
Yes.
Except that if the reconnection occurs, if the jet originates at different altitudes, then different species are ionized. So the jet picks up different ions according to their...
In the past, I've had a lot to say about that model. I don't believe it's, in principle, what they're talking about can happen, but it doesn't give the correct fractionation. All they treated was silicon and neon.
Okay, crudely speaking, it does a similar thing, though, right? It picks up some ions.
It'll pick up ions, but it'll give you a mass dependent. They haven't got the correct charge exchange coupling. Yeah, there are a few other, it does happen, but it's not the explanation for what I'm talking about. Okay, two more derivations. You can take the polarization and magnetization produced by the waves and calculate a force, and also the change in the dielectric constant produced by the passage of an Alfvén wave. These only depend on the refractive index of the wave. So it's clear that wave refraction is important. And then, of course, you've got when I finally found this, the way Arthur Ashkin describes it with his models of waves propagating through atoms. And the final sort of conclusive proof that I think I'm right comes from a paper by Deborah Baker and Marco Stangolini. Deborah has made a map of the corona showing Fipp fractionation in these yellow points. And Marco discovered Alfvén waves in the chromosphere from oscillations in circular polarization. and one of the two did a potential field source surface extrapolation between the chromosphere and the corona. And guess what? Regions of high wave activity in the chromosphere match up with regions of high FIP fractionation in the corona. So aside from the fact that my model gets the answer right, some of the things that must be happening in the sun that when I first thought of this in 2004 weren't observed are now beginning to be observed. So this was very, very satisfactory to me. I was actually very, very happy when I saw this. So not wasting your time. Okay. They're really linear Alfvén waves. I don't have any non-linearities in this. You can put turbulence in, you can have waves interacting, but it's not. Sunspot, yeah, this is going to be a few thousand. Yes. Yeah. I don't know where the waves are originating. I know in the coronal, in the closed loop, I believe the waves originate in the corona by a nanoflare. But in open field, they presumably have to originate as waves coming up from underneath. Okay, that's the FIP effect. And now I advertise inverse FIP. When you look at stars, you get a more complicated view. Here is a plot of 1 over, logarithm of 1 over the FIP bias. This is made by my colleague Brian Wood. So the sun with a FIP enhancement of 4 appears at minus 0.6. Notice stars of similar spectral type to the sun have similar abundance anomaly. As we go to later spectral type, FIP bias decreases, goes to 0, and then becomes inverse FIP for the M dwarfs. This is something that nobody else could explain, not even Dermot Mullen and Nick Arge. But we can address it with the ponderomotive force. And I also put up a paper here by Balincelli et al., who have a much more modern, comprehensive, they have about 60 stars, and they have various statistical techniques, and that this basic correlation survives. How do we get inverse FIP? They all have hot coronae. Not all of them have known photospheric abundances, though most of them do. And that's what Selly et al. Did. They did a comprehensive job on finding the best sets of photospheric abundances they could. It's a particular problem for M dwarfs, because the photospheric, the optical spectrum is full of molecular bands, and it's very hard to dig out the atomic lines that you need. But you know, with a bit of hard work, it can be done. So how do we get inverse FIP? Well, I want to go through some of the sort of diagrams that Arthur Ashkin drew in his original paper, just to explain in detail the microphysics. So we've got we've got a magnetic field going up this way, and there is a gradient of the wave energy density. It's going down as you go upwards. So consider a wave here entering an atom or an ion which we will describe as round, and it refracts like this. This will push the ion upwards as the wave is pushed downwards. Consider another wave coming down from on top, doing the same thing. This will push the atom downwards as the wave is refracted upwards. And if this wave is stronger than this one, which is the usual case, you have a net upwards force. So parallel propagating waves or close to parallel propagating waves give you positive FIP effect. This calculation is done for fast mode waves because it's easier to manipulate Snell's law and things like that. And you get roughly the same expression I had before, but with an extra 3 pi over 8, which is due to the approximations I had to make this analytically tractable. Here is the case where we have inverse FIP. It's the same setup as before, but the waves are now propagating perpendicular. This wave refracts this way and would push the ion down, and this wave would do this and push the ion up. So the net force, if this wave is stronger than this one, is a downward force on the atom. This is where the inverse FIP effect arises. This could be Alfvén or magnetosonic waves. This must be fast mode waves or magnetosonic waves to give you a negative fractionation. So where do these fast mode waves come from? Here I'm showing you the diagram I showed before, but I've included now waves that are coming up from underneath and being refracted down in the region of increasing Alfvén speed in the chromosphere. This can happen below an open field or below a closed field. This is where, thank you, this is where the inverse FIP happens. It turns out that convection gives you a wave amplitude here of about 1 kilometer per second. That is not enough to cause fractionation. It needs to be about 10 kilometers per second. And let me see what I have. I'm going to skip this in the interest of time. This is the solar FIP, inverse FIP in the sun. And go to this plot. Here is a plot of some of the same stars I showed you before. We have the magnetic flux in the photosphere. We have their Rossby number. So Rossby number, let's get this right, it's rotational period divided by convective overturn time. So the faster rotators are on the left-hand side of the plot. So as we increase the stellar rotation, the magnetic field increases, and then it saturates about here. The important point is that on this branch of the plot, all these stars have positive FIP. And as we get to the where it saturates, the stars have inverse FIP. And if you consider that the magnetic field that's generated by the dynamo is being destroyed and turned into waves, and calculate what that wave amplitude should be, it's around 10 kilometers per second in the chromosphere, which is about enough to cause inverse FIP. So this is the origin of the inverse FIP effect. It's magnetic field generated by the dynamo, not making it to the outer layers of the star, but being destroyed and turned into fast mode waves. So conclusions. I'm just going to go through this very quickly. Quantum motor force is the key mechanism. This is a little bit of a different situation to solar coronal heating, where we have many mechanisms. And when we find the answer, it's not going to be a clean answer. It's going to be a whole assortment of things. I believe the quantum motor force is the relatively clean mechanism for ion neutral separation. Different magnetic geometries give us all the variations so far observed, and there are more variations I haven't described to you, but they do come out of this. There are novel diagnostics of waves, observational correlations between Alfvén, the postulated waves, and the abundances of ability to be seen. Something similar is seen in the corona around accretion disks, or above accretion disks around black holes, suggesting that astrophysics is what determines the saturation, not the driver. And I'm happy to answer any more questions. I've just given you a top-level view, and I haven't included any of the details of how the calculations are actually done. So I'm happy to answer that. Thank you.
More questions? Yes, Andrea.
So which should be the gradient of wave energy that you want to height to get a correct feedback?
What should it be?
Yeah. I imagine it's the energy density that matters.
It's the energy density that matters. I don't have it in energy density terms, but typically in the chromosphere, where the fractionations happen, you need a wave amplitude of around 10 kilometers per second.
No, fine.
But yeah.
We have the downward propagating mode, which is more rapid than the upward.
Yes. Well, I can't give you the wave energy density, but the pointing flux associated with the waves is around 10 to the 6 ergs per square centimeter per second. It's around the same sort of fluxes you need to heat the corona or accelerate the wind. It's.
Because in my experience, since you have the transition region up there, which is extreme reflector and refractor,
Yes.
your energy density of waves going up and down is about the same.
Yeah.
So you need a very tiny difference to get this. That's what was the question.
Yeah. Now, for the resonant case, I didn't show you the. If we were here in a resonant case, typically you have the waves are going backwards and forwards at the same going each way in the corona. But in the chromosphere, you have one mode is more dominant than the other. Well, basically, you feed waves in at one amplitude, one side, integrate the equations, and a small amount leaks out here. That's roughly what's going on. You do have some, I mean, you have more imbalance in the chromosphere than you do in the corona. And that's on the assumption that basically the waves are being generated in the corona, and a small amount leaks out at each end. Yes, yeah. And I think you need coronal generated waves to guarantee the resonance. If you had waves coming from underneath, you wouldn't, you know, you... Yes, yeah. Well, the neutrals don't see the MHD wave.
But it still passes through.
It passes through them, but the MHD wave sees charged particles. The neutrals don't come into the MHD dielectric tensor.
So it
has no effect. I mean, it will have some effect by polarization and things like that, but that's second order. That's... Well, yeah, the collisions are already in here. I didn't go through those details, but...
Okay, so let's move to the next presentation. And let's thank again. So Gongli is the next speaker. And he's talking about the meandering nature of the solar wind magnetic field. Or the solar magnetic field, maybe not solar wind magnetic field.
So you have to bear with me again for the second time. This time is for my own presentation. So before I start my talk, I just want to show these two pictures. This turns out to be last year, November 15th, and this is this year today. It's actually just this pathway coming up. So what I learned from this is human activity actually has a correlation with nature, but for turbulence people, we can do this differently. We can do that's open. Yes, because they trim all of the trees, right? No, because they have no tourists. So global warming actually makes because we have so much human activity. So what I'm going to talk about today is it's about the Parker spiral field. So what I want to do is to sort of tell you what can make this Parker field non-Parker, and I'm going to focus on one particular mechanism to make this non-Parker, which is the foot point motion. The Parker field actually, the good Parker field is the consequence of these three things. Frozen-in condition, which basically says the path of the scaling magnetic field out. And then this constant rotation, otherwise this Parker field can go back and forth. And then there's constant radial speed. This is important. If you actually have variation, you can get switchback. So this goes to 1966. Wilcox had this paper. You actually look at this change of this sense. So if you look at the magnetic field change, radial magnetic field, and then you measure this correlation of this radial magnetic field from this photospheric magnetic field and this in situ magnetic field, you can deduce the speed. And because if you have 4 days, you can know this is 400 kilometers per second. And then by making this assumption, this frozen in, then you will get this nice Parker field. So you know the Parker field once you know the rotation. And then you can actually look at this Parker field using energetic electrons by looking at this particular source at the sun. That's impulsive flares. So you actually can know pretty good about this configuration of the Parker field or non-Parker field just using this correlation between the source of energetic particles, electrons, and this in situ observation of energetic electrons. Now, to go to non-Parker field, you have quite a few different So now that actually offers you one way to tell how non-Parker magnetic field can be. So what you can do, you can use ionizing electrons, measure statistically what these path lengths are for positive SET events. And then you look at how this spread is, and then you know how non-Parker it is. So this involves with this so-called fraction velocity dispersion analysis, which actually I talked about that last time when I was here, last year. So it's involved this analysis. I'm not going to go through that, but just to tell you this is basically the velocity dispersion analysis, but you can use the whole rising phase of different fractions to get a very accurate measure about this path length. So what happens is, go back. If you actually compare all of these particular three different distributions for different eta, if you compare it with some model calculation, which I'm going to show, you can actually get an estimate about this one particular parameter which I'm going to use to characterize how this non-Parker field is. So the other thing I'm going to talk about today for the non-Parker field, I'm going to talk about the foot-point motion. That is what I'm going to show first. The observation is going to find the non-Parker field, at least from the point of view of path length, doesn't differ much from the Parker field. So that tells you if you use the Parker field in your analysis or your observation, that's okay to the first order. So this was a pretty old paper, goes back to 1999. The Jagiellonian geography, they actually have a way to describe this random foot point motion so that you can get this interplanetary magnetic field, which is non-Parker. And the way to do that is you do this Helmholtz decomposition, and you assume this velocity field actually can be given by two different, in this case, you can this divergence free case. You get just one of this psi, which is basically a field, which is a global field defined in all the sequence line, and you can look at what happens about this, the velocity field at the source surface. So we did that. In the Martin Lee paper, we actually just did this multiple YLM expansion and look at this velocity. This is coming from that field beside here, the velocity on the source surface. And then you follow each of these individual individual plasma, then you can actually get this non-Parker field. So this will be the foot-point motion. So any given foot-point motion on the source surface will give you a field line, interplanetary field line, which is non-Parker. And you can measure how non-Parker it is by looking at the path length and this sort of deflection of, if you use the ionizing electron to look at the deflection from the original Parker field to the final Parker field. So this shows you this electron trajectory along such a non-Parker field, and this shows you about for one particular parameter which I didn't specify here, you can get about 10-degree deflection about this. So if you look at this energetic electrons, the best connection, if you go out by 10 degrees, you can still get to being observed. While you, for one particular parameter that we put in this model. So it's pretty good. So this is a comparison I mentioned that one particular parameter turns out to be this so-called VRMS. So it's this, which I call VG here. So it's basically measure how fast the foot point is moving. It turns out to be 1 kilometers per second. So now let's actually look this Jagiellonian geography field for a little bit. Let's think about what it is. It actually requires you to have a global distribution actually take this approach. You can actually plot field lines. This is somewhat different from the JJ field. And then you can look at this. So this is, you can also calculate angular separation here. Again, by a single parameter. This gives you one model of this. However, once you take the assumption, this is a diffusion, so yeah, this shows you angular sort of spreading. You can treat this like on my size distribution or just back Gaussian. It's reasonably good description about this, this SEP, solar energetic electron spreading. However, there is a very big issue with this field. This is the path length. So if you were to compute the path length for a diffusion model, you're going to have trouble because you'll find this goes infinite. You can easily show this by assuming fixed distance from your source to your target. You make this step size smaller and smaller. The diffusion basically saying the number of steps is going to time to get this enhancement going from this point to this point, which has distance r. It's going to be enhanced by the number of steps it's going to take by r or lambda. Now you take lambda smaller, this whole thing go up. That's what happens to the coastline length of the England. So what's going on here? So let's look at our assumption about this foot-point motion. So you can actually look, instead of this total Planck equation, you can look at this foot-point motion itself. This is what happens, right? dr dt, this gives you the velocity. If you put this side to be 0, you get partner. Nice rotation, right? So if you write down this diffusion process, you say delta omega, which times this r, it's going to be the delta v, is going to be this, whatever is parameter here, and this is random, this is putting this random sort of vector here. So you put this into a white noise, having this delta function, then this gives you diffusion. That's easy as that. But if you think about it for a little while, you realize if this is random sort of vector here, and this fixed sort of length or magnitude, you basically changing the velocity in a very, very short period of time. So you really need acceleration to infinite. It's non-physical, right? So what you can do, you can just say, no, the velocity cannot change randomly at a very short period of time. It has to change gradually. So you introduce an intrinsic time scale tau. So you can put in this delta function. This is broader. This is one way to get a broader function, delta function. So when you realize when you do this, this becomes non-Markovian because you actually depend on this time history, reading this little tau. You stare for this for a little while, you realize not only it's non-Markovian, it's actually an Ornstein-Uhlenbeck process. So what you do here is to say this is not infinite. I'm going to make this continuous here, but I make this acceleration going to have this piece, random piece. All of a sudden, everything is well behaved. You're going to have differentiable path lengths. It's going to be integrated. You're going to get finite path lengths, but you're going to retain this diffusion at a long time scale. When the t is much bigger than tau, you're going to retain this ground motion. So what we did is we basically claim what happens. The random foot-point motion is not random at very small time scale. It's actually governed by this OU process. We put in that. This is what the foot-point motion now looks like. It now actually looks more like to this JJ field instead of the diffusion. So it's differentiable. It's nice behavior looking. And this is the corresponding interplanetary magnetic field line corresponding to this foot-point motion. You integrate, you get your path lengths have these distributions. Again, this now has a random piece in that because the acceleration has a random piece. So you can write down this minus expression because velocity has no infinite piece, so you can just write down this. So to summarize, what we did is we looked at this how you can expand a particle field to a non-particle field. And I showed So the bottom line is Einstein-Uhlenbeck process, which goes back to 1940s. So it's actually a reasonably good process which can be found application in solar physics of stuff here.
Thank you.
So how about if during this foot point motion, locally turbulence, there is some local stronger connection events. So there is recombination locally during the expansion with timescales that are very fast. Then is valuable or useful?
There is a way to say that. It turns out we consider what happens to this the so-called lifetime of this foot point. So if you consider a region where you allow them to die and to reborn, so this is like super granular in their lifetime. So if you allow them to have reconnection, but within a certain sort of region, then you still can model them by putting in multiple foot points inside that little region to model how spread they are. But in a way, whenever you regenerate a new field line, you just set this power t equals 0 and then regenerate another field line. So long you know where it's going to regenerate.
I understand that there can be a random walk of the foot points, but the way this information is traveling longitudinally along the magnetic field, it depends on the solar wind physics. So this is what you call the turbulence. This is what you call the turbulence in the solar wind.
Yeah. So let me add that slide. What I mentioned at the very end is, if you look at locally, the fluid parcel actually moves in a stochastic manner exactly like a foot point. So this figure shows, so we actually, if you do this in a Lagrangian point of view, it's much easier. But this figure shows if you actually have no in situ turbulence, what happens in the foot point is just random, not random walk. You OU process, you could map out this field line. This is no in situ turbulence.
No solar wind.
No solar wind turbulence. Once I put in solar wind turbulence on top of this red line, I'm going to get another greenish motion corresponding to different parcel, which with a different history. It's described by exactly the same OU process, except it's not spherical, but it's only, it has to be done locally at that particular magnetic sort of background magnetic field at that particular location.
Okay, but the red line will depend on, for instance, on the speed.
And this red line only depends on the speed of solar wave. Once I put the green one, it depends on the offense speed. So there will be another piece. This one is most important because V is much bigger than VA. But we do have another paper which is actually including sort of description about how the magnetic line really looks like if you put it in the specific surface.
Another question? Bill.
I'm just wondering, John, the second class that you're talking about, the in situ turbulence, that I take it corresponds to the version we Ukrainian colors.
What?
These are Ukrainian colors. You like them?
Yes. Okay, I'm Luca. Can you hear me even without?
Yeah, but it's
phone?
easier for the streaming. So
Okay. Sorry. Okay. Okay. So I'm Luca Barbieri. I am a PhD student at the University of Florence, and I'm going to present this work in progress in collaboration with Andrea Verdini and Simone Landi, and Lapo Casetti, that is a professor of theoretical physics, statistical mechanics here at the University of Florence. Okay. Okay. The main problem of solar physics is, of course, the coronal heating problem, where the problem is how to explain the shape of the density of the temperature in the sun atmosphere. Because as you can see, you have an outer region that is the corona with a temperature that is very big with respect to the inner region. There it is the chromosphere. Okay. The standard approaches to study this problem are fluid dynamics approach. The main problem of this approach is that they make the hypothesis of local thermal equilibrium, and this does not same equilibrium states. And so there is an alternative approach to the fluid dynamic approach, that is the Scudder approach, introduced by Scudder in 1992. The idea is very simple. You consider the atmosphere as an ensemble of non-interacting particles, so a standard one species atmosphere, and the model is one-dimensional, no interaction between particles, but you impose a stationary boundary condition. So at the base of the atmosphere, you impose a suprothermal velocity distribution function. If you do that, since the particles are non-interacting, the shape of the distribution at another height and another height going up in the atmosphere is totally ruled by the single particle conservation of energy. So, starting from the base, where you have this distribution function, you can build up the distribution function at this height using conservation of energy and saying only the particle with velocity that is great then this level can climb up the potential well and constitute and build the atmosphere at this level. And then you go on. If to build this, to construct the distribution function at this level, you use conservation of energy, and only the particle with this velocity, that is greater than this level, can climb up the potential well and reach this height and form the velocity distribution function. Why is important to put this suprathermal velocity distribution function at the base? Because if you plot the logarithm of the velocity distribution function divided by the number density as a function of the kinetic energy, you'll see that using a suprathermal distribution function at the base, you have the variance, the standard deviation of the distribution function increase with the height. What does it mean? That when the density decreases with the height, the temperature rises up, because the kinetic temperature is nothing but this variance. What's the problem of this approach is that there is no physical argument to justify in a very good way the presence of suprathermal velocity distribution function at the base of the sun atmosphere, because there the collisionality is very high and we expect to find thermal distribution, not suprathermal distribution function. Okay. Recently, it was introduced an alternative approach, another alternative approach in another field, the statistical physics, in particular statistical physics of systems of particles with long-range interactions. They find a new mechanism to produce temperature inversion. So what is a system with long-range interaction? A system of particles where the potential between particles behave in this way,
What does it mean? That the particles does not interact only with the nearest neighbor, but with all the particles of the system. In this limit, the relaxation time to thermal equilibrium of this system diverge with the size of the system, especially for gravitational system. This time is much greater than the age of the universe, so they stay out of thermal equilibrium. The interesting thing is that the collisionless dynamics, that is the dynamics that rules this system because they are out of equilibrium because of this condition, is the Vlasov equation. So it's the same differential equation that rules collisionless plasma. Sorry, small d is the dimension of the physical space. So for the ordinary space, this is three-dimensional. Coulombian potential and gravitational potential are long range in principle. Okay. The mechanism that I have proposed for long-range interactive system is the sequent. You take a system of particles with long-range interaction. You initialize the system of thermal equilibrium and you let the system in thermal equilibrium. This is a macroscopic observables of the system, especially this is a specific observables, but it could be also to be concrete, the mean kinetic energy of the system as a function of time. You initialize the system of thermal equilibrium, so the system stays there. Okay, at a given time, you inject energy into the system and it relaxes towards a non-equilibrium stationary configuration due to collisionless dynamics with temperature inversion. So the density rise up and, the temperature rise up and the density goes down at the same time. What's the problem of this approach? This was introduced for a toy model with, yes? Theta is the spatial coordinate of the system. Theta is the spatial coordinate, like the x in the Vlasov equation. So with the distance, so suppose that this is for application in an atmosphere. This is the base of the atmosphere. This is the top of the atmosphere. When the density goes down, the temperature rises up. So, but what's the problem? This is a mechanism created for system with long-range interaction with only one species. So there is no repulsion and attraction between particles. So it cannot directly be applied to plasma. And in particular, is true for isolated system. So you cannot apply directly to the sun atmosphere because the sun atmosphere, the outer layers are in thermal contact with the inner layers. You have a thermostat at the base and the system is not isolated. The solar corona, of course, is not isolated. What? At T equals 0, the density is uniform. It's like an isothermal atmosphere configuration. Okay, so let me go on. Okay, so what did we do? We introduce a new kinetic model of two-component plasma. So we take into account electrostatic interaction, and we put it at its base a thermal contact with the chromosphere. So we model a plasma atmosphere, and at its base we put a thermal contact at variance with scatter that puts suprathermal boundary condition. When we introduce a theoretical procedure where we introduce fluctuating temperature of the thermostat, so we vary with a specific procedure the temperature at the base of the atmosphere, and we will show that the system undergoes oscillation towards a configuration with temperature inversion. Then we introduce an analytical model to explain the results of the dynamical procedure that we have implemented in the kinetic numerical model. And finally, using this model that explains the results of the dynamical procedure, we make the application to the solar corona. Okay. The model is the sequent. we have considered a specific structure in the sun atmosphere that is a coronal loop. So we have schematized the loop as a basic semicircular tube, and we put it in contact with thermal contact with a thermostat at the base that schematizes the contact of the outer layers, so the transitional region, and the corona with the inner layer, the chromosphere. Okay. We do not consider the mean field magnetic field, because the only role that we expect is to confine the plasma in the loop and do not contribute to filtration up to the top of the system. We have included the gravity due to the sun as the standard gravity, uniform gravity of an atmosphere, plus the Pannekoek-Rosland field. Finally, to schematize the electrostatic interaction, we impose cylindrical symmetry around the principal axis of the loop, so the problem becomes one-dimensional. And using this cylindrical symmetry, we could stall from non-equilibrium statistical physics the HMF assumption that permits us to treat systems that with large scales. If you consider a realistic plasma, the scale of the physical plasma is much larger than the Debye length, so it's a macroscopic system. In this case, you can apply the HMF approximation, and that consists in taking the large-scale contribution of the electric field, so retaining only the first Fourier mode in the expansion in Fourier mode of the electric field. Okay. This is very useful because the computational cost of this simulation reduces to n, starting from n square, that is the standard computational cost of a basic n-body simulation. You can reduce it to n, the computational cost. So, in practice, we have a model of two-component plasma with an external field, that is the gravity Q plus the Pannekoek-Rosland field, in thermal contact that schematizes the corona, the atmosphere of the sun, starting from the transition region up to the corona, and we put it in thermal contact with a thermostat. Okay. This is just a technical slide. This is the system of units that we have used. We have normalized the system to the length of the loop, the first Fourier mode, the velocity to the thermal velocity at the temperature of the chromosphere, 10,000 Kelvin, and the mass to the mass of electrons. Doing that, the system is fully described by three quantities: the mass ratio of electrons and ions, this quantity that is nothing but the thermal crossing time divided by the plasma electron period to the square, and a stratification quantity that is the gravitational energy divided by the thermal energy. Okay. Using this two-component plasma model in an external field, as we said, we put a thermostat at its base and we start the dynamical procedure. So we initialize the system in a thermal configuration, so as an isothermal atmosphere configuration. We let evolve the system for a given time in this thermal configuration, it stays fixed. Then for an interval of time delta t, we increase the temperature of the thermostat. Then we put the thermostat back to the original temperature, so the temperature of 10,000 of Kelvin. Then we rise up again the temperature and go on procedure. We put back at the initial thermal equilibrium and go on. We rise up the temperature. So that's the procedure, Dover, where the time delta t and tau e has been chosen such that for the interval of time delta t has been chosen that is lower than the relaxation time to equilibrium at temperature T. Otherwise, if I let the system for an interval of time such long that relax to this configuration, this is the results that I'm going to show are no longer true. At the same time, when I switch back the thermostat to the initial temperature, I choose these time scales to be slower than the relaxation time to the initial thermal equilibrium. In this way, I never let the system coming back to thermal equilibrium at time t or at temperature T or at temperature T0. Okay. A distribution function. I'm going to show now. Okay. Okay. About the time between two perturbation of temperature, the time is not constant, so this time tau e are not constant, but are taken from a distribution function, that is this one. That is an exponential distribution. That means that we model the temperature fluctuation of the thermostat as collision in a standard gas, so causal random events. And for the intensity of temperature perturbation, we have chosen another exponential distribution that is the worst case. So the lowest temperature are the most probable. Okay. Using this procedure, we show that the system that is initially at thermal equilibrium, when we start the dynamical procedure, is set out of thermal equilibrium. Yeah. Okay, 5 minutes. Okay, no problem. Is set out of thermal equilibrium and it relaxes to a non-equilibrium stationary configuration. This is the trend of the kinetic energy of electrons and ions as a function of time. So the kinetic energy rises up, but it stops to a non-equilibrium thermal configuration with temperature inversion. This is the spatial coordinate, this is the base of the loop, this is the top of the loop. When the density goes down, the temperature rises up. Okay, so how can we interpret these results from this numerical model? We have introduced a numerical model to describe the shape of the distribution function in this quasi-stationary state that the system achieves. What's the idea? For an interval of time delta t, the temperature rises up, and the thermostat in this interval of time is fixed with a thermal distribution at this temperature. In the interval of time tau e, the thermostat is fixed with the temperature of the chromosphere that is 1 in our system of units because we have normalized the temperature of the chromosphere to 1. The average over the quasi-stationary state, the temporal average of the different thermostat during this interval time, and this, and this, is the sum of the convolution of all the thermostat during the perturbation, weighted with the distribution of temperature that we have chosen, plus the equilibrium distribution of the chromosphere of the thermostat during the interval of time tau e, tau e, tau e. Okay. The weight of these two populations, this multi-temperature population and this other population, is the fraction of time during the stationary configuration when the system stays in this multi-temperature configuration, and the fraction of time when the system stays at the initial temperature. So we have a formula for the boundary, so the fluctuating thermostat. We have a formula for the fluctuating thermostat. We can use the static formalism introduced by Scudder. The system goes into a stationary configuration that must satisfy the Vlasov equation. So using the Jeans theorem and having the boundary, we can build up the full distribution function of the system. So we have compared the results of this model with the numerical model, and for the moment the results are quite good. Okay, the agreement of the density profile predicted by the analytical model matches fairly well the results of the numerical kinetic model. So we are trying to use the analytical model and apply it to the sun atmosphere. Okay, so we take our analytical formula, we substitute the realistic number, and we do a loop that goes up to z, up to the base of the transition region to the height corona. I will show you the number in the next slide. And we substitute the realistic number. What we get is the following. Okay, we obtain a density profile with a first part that is quite similar to the shape of the transition region. And then the last part that is similar to the shape of the density in the corona. The same for the temperature. This can be interpreted in this way. If we plot the distribution function at the base of the system, we have two parts. A central part, the green, the distribution function at the base of the system is the green one. A central part that is Maxwellian, and is due to the fact that we put the thermostat back to thermal equilibrium for different instant of time, and high energy tails. Applying conservation of energy, during this part, the central Maxwellian cannot climb up the potential well up to this height, and so the central core, the central Maxwellian core tends to disappear. At the end, in the corona, we have only suprathermal distribution function due to the fact that we have many temperatures in the system. So, as a conclusion, what we do, we have introduced a new kinetic numerical model of two-component plasma, and we put it in contact with a thermal boundary. We have shown a dynamical procedure where we introduce thermal fluctuation, temperature fluctuation at the base of the atmosphere. Finally, we have presented an analytical model to interpret the results of the dynamical procedure, and we make an application to the sun atmosphere, obtaining a shape of the density and the temperature that is qualitatively similar to the ones of the sun atmosphere. So that's it.
But the electron can thermalize along the main field, along the magnetic field.
maximum that you reach there. This is the top of your loop over there. The 10 to the 5 is the top of the loop.
Yes, the 10 to the 5.
Okay. Okay.
Is more or less 2 million of
Yeah. It would be really great to see how this could be applied to a solar wind, where you just cut the loop when you let the plasma. Because if you can explain non-thermal distributions in the solar wind from this mechanism, this would be a big result.
Okay.
Yeah. Okay, thank you again. No more questions? So, Simone, when is the topic? When is the
Should be now, I guess, because we are one late.
They are ready, I've just been there to take the classes.
Okay, we have two persons.
No, we have.
We have to take a coffee break now.
No, we have 1, 2,
30
3. We have 3 talks plus Sohom. Sorry?
Okay.
We have Pet, we have Emanuele, we have Pauline, and we have Sohom.
I'm Sohom.
You are Sohom, so we have 4 more people.
Yeah, I know.
So you decide when is the break.
Now.
Now, okay. How long?
30 minutes.
30 minutes break.
Really 30 minutes. 30 minutes. Sharp.
try. Would be.
Let's see if it works. Try to talk.
Hello, hello.
Perfect.
Do you hear me?
Yes. So you put this on your set.
Okay.
No,
There is a yeah.
I think he was only able to get this right now.
Yeah, probably. Hmm.
Speak louder. Speak.
Yes.
Okay, we're gonna see if it works.
Okay. I am local. I have some. Okay, no problem. But see you tomorrow. No? Come on.
Okay, we are missing Bill.
Yeah. Oh, that's. I hope nobody important.
Maybe nobody.
Yeah. No. Yeah.
Okay, so Pat, I think you should start.
Okay.
People
Good.
will come as you start.
Good afternoon. I hope the micro works. So I've got kind of tired from all these energy cascades and pressure dilatation, pressure strain effects. So I thought it's maybe time to look to large causalicity turbulence in the solar wind, so fast solar wind or alphanix slow solar wind. So
Could you use the microphone? Or? He's using a microphone.
I have this. I hope it works.
Okay, never mind. It works a bit.
So the motivation is we have this high causalicity flows, those fast solar wind or the alphanix slow solar wind, where we have to look at the energy and the causalicity together, and we expect to see there is a cascade of energy and there is a simultaneous energy cascade of causalicity. And mostly this situation is studied within the MHD regime, and we are interested what happens when we add the whole term. So what are the new things that are that happens when you add the whole physics? So
I will show you one simulation, results from one simulation, and it is a simulation that was done more or less with ad hoc parameters by Emanuele. So it's a simulation with these parameters, and most importantly, okay, it's a relatively large beta, so it's weakly compressible, and there is the relative causality is 0.5. We have some and it's whole MHD, compressible whole MHD simulation, 2D, and we have some resistivity, viscosity. We put some large-scale alpha-Nick-like fluctuations, and we let the system evolve. So this picture is the standard result of a turbulent simulation. So we have the black line shows you the magnetic power spectrum. The blue one is the kinetic power spectrum. And the line is the important minus 5/3 spectrum. So we have some sort of nice power spectrum. Now we can start to analyze this simulation. And before we look at the causality, we start with the Jaglom, with the Kalman-Haworth-Monin equation for the energy. And we use, so what you do, you define your second-order structure function, where you characterize the kinetic energy distribution using increment of W, where W is the square root rho time U. So this is a way how to include the density into the picture. And this is something that was used by Orsak a long time ago. Okay, you use these increments, and then you define the kinetic energy contribution and the magnetic energy contribution. And you just take your compressible Hall MHD, and you can obtain this equation for the time derivatives of this, this is an equation that is valid. It comes from the equation. There are some assumptions, homogeneity, so that you have a closed system. And you have terms that contains the MHD nonlinearity, the Hall nonlinearity. You have a term with a pressure dilatation, and you have a term with dissipation. And this is valid, but when the interpretation of these different terms makes good physical science mainly when you have developed turbulence, when you can interpret this as a term describing the MHD cascade, the MHD cascade rate, and this term that describes the whole cascade rate. So we can take this and look what we get from the simulation. So we take the simulation results, we define these different terms, and we also define this is not 0, this is O. This is a characterization of the error. It should be 0, but because all these numerical things that happens in the code, in this case, okay, there is a small error, and it's sort of negligible, and it's mostly because the way how we estimate this, because we estimate it just by finite difference between two outputs. And the outputs are relatively far away. So this term should be 0, and more or less it is. And then we have this different terms. And okay, they are given as a function of the separation scale, L. So this gives you that the blue term gives you the time change of the second order structure function. So, and this is naturally interpreted as a decay term. So this, yes?
When you say separation scale, separation between
you defined your quantities as 2 points separated by the separation scale L. And then you have this difference, and then you calculate this average over X, so you have dependence on L. And this is a vector, and we integrate over the angle into D to have 1D picture. So this gives you that on large scales, the dominant term is the K1. So this gives you that on large scales, this is a decaying situation where we put initially some fluctuation on large scales. So this term just says that the energy is leaving the system, well, is leaving these scales. Then you have a green, so in the middle, the dominant term is the MHD cascade, right? Then you go to smaller scales, and then the MHD cascade is, decreases, and it's partly replaced by the Hall cascade. So there's onset of Hall physics around here, and around KDI1.
Sorry, a nice question. So on the large scales, if I look at the curves, there are general trends and kind of small fluctuations.
Yeah.
Why there are small fluctuations on the large scales, while I would like to say that I have more small fluctuations on the small scales?
It's just you don't have that many large scales. It's this case. So, and so this is just kind of, this is a residue of the initial fluctuations. So we have this term where that the MHD cascade dominates, and there is some contribution of the pressure strain effect. So there are some, this is basically the fact that the plasma is compressed and it expands, and it gives you some energy exchanges between the kinetic and magnetic energy and the thermal energy, or internal energy. And everything is balanced by the dissipation. So here in the middle, this term dominates, and this is where we get close. This is the closest way we get to the inertial range. We don't really have inertial range, because in the inertial range, we would have this cascade rate compensated by the dissipation rate. But unfortunately, the box size is limited, and it doesn't really work that well. But we are not that far away. Well, it's not that bad, let's say. So now, if we look at the cross-helicity, so we can define an analogic equation for the cross-helicity, where we define cross-helicity as, okay, this is a second order structure function that describes the cross-helicity, the distribution over scales. And you can get the same structure where you have this term gives you the decay. This is MHD cascade. There's a term that is analogic to the whole cascade rate for the energy, but there is a question mark that is a small spoiler for the, and that there's the pressure dilatation effect, which is a little bit different from the energy.
Don't you spoil the... I was expecting somebody will do it. Okay, so yes, but we start naively with this, yeah, we have that. Well, the thing is, of course, first, okay, there's the dissipation, but this is okay, but in the compressible case, you have another source of non-conservation. And the second part, this is another part where the causality is not conserved. So, but anyway, we can do it. We can do the calculation. So the same picture, so the kind of the error, which is about 0, the back line. Then on large scales, the blue line gives you, you have losses of the causality on large scales. Then there is a part that gives you a nice cascade, right? 2D. To simplify things, because... And then there's a small pressure dilatation effect, but it's basically not negligible. Basically, it's almost negligible. But interestingly, the whole term is kind of negative everywhere and slightly positive here. So this whole physics seems to work for it doesn't start here. It works everywhere. It seems.
It seems that it's 0, or if you look on logarithmical scale, it's not 0. At MRD scale.
Which one?
Oh no, sorry, this is very small scale, right?
Yeah, you have small scale, large scale.
Okay, sorry.
So, of course, as was the good remark, is that it's not a good idea to really look at the causality in the whole MHD. If you look at if the causality is an invariant or ideal invariant, you see that you have equation for the causality. There is one term, which is the whole term, that doesn't disappear if you average it. And okay, this is the way how the pressure dilatation works on the causality in the compressible case. And you have dissipation. But what you can do, if you look at the kinetic helicity, it has the same kind of term. So if you do a combination, so this is generalized causality, X-helicity, as you get rid of this and you just have dissipation and pressure dilatation. So we should look at this. And one of the points here is that the whole term couples the causality and the kinetic helicity. Okay, this is mass over charge. And okay, if you rescale it, okay, if you do the classical rescaling, this is di over 2. Yeah, this corresponds to di. So this is, again, something that suggests that everything works below on ion scales. So now we formulate this equation for the X-helicity, where we no longer have the whole term, because it disappears, because it gives you the exchanges between the kinetic and the causality. So we have this, and then if we look at the result, so this is quite similar. So this is the result for this generalized X-helicity. So we have this, again, error. Again, on large scale, you have losses. So the energy that is being lost, that continues through the cascade. And so the MHD cascade works quite nicely in this case. And all this is balanced by the
dissipation. And typically, you may expect that the pressure dilatation thing are not really important for the cross-helicity. Now, if we now look at the cross-helicity, well, this is the power spectrum. The black is the magnetic power spectrum, the black line. It's a function of KDI. Yeah, I am there. And then if you plot over this, you can define the co-spectrum of the cross-helicity, the co-spectrum or cross-spectrum, I don't know what is the proper name. So this is the cross-helicity, the kinetic helicity, you make the sum. There should be some factors to put it correctly. So the green line shows you nice co-spectrum for the generalized, so for this x-helicity. And if you look at the absolute value of the kinetic helicity spectrum, you have this solid line gives you the positive part, which is above KDI1. So this corresponds to this positive value of this effective MHD, effective Hall cascade rate of the cross-helicity. But on large scales, you have negative cross-helicity that corresponds to the negative value of this coupling term. So, and it's really, I think it's quite interesting that this coupling works all over the space. So it works even though the amplitude is not that big, but still there is a coupling between cross-helicity and the kinetic helicity in the whole MHD. That is not constrained only on subion scales. So is it important for the dynamo? Could be.
She was investigating this whole MHD dynamo, and it is more efficient.
It's actually Pablo Menini's PhD thesis.
Okay, so it's well known, except not so well known. But here I show you a way how to quantify the scale dependence of this coupling using this Kalman-Haave-Monnin equations. So we have a cascade of energy, we have a cascade of x-helicity, kinetic helicity, and of course it was only 2D, so we should do things in 3D. And if we just go, the next direction is to check this behavior in hybrid simulations, because this sort of pressure dilatation, the magnetic pressure dilatation thing, should translate to some pressure magnetic strain effect. Okay, thank you.
Very nice. I mean, people don't recognize the existence of these other variants. And I can't help but think that what you've done here is a step in the direction of understanding this kind of slightly strange claim that some people made about helicity bottleneck. I mean, I don't know anybody,
yeah,
people that I hang around
exactly.
with don't really buy into that idea. But I think you're pretty close to explaining it here. I think it's that the physics of the cascade has changed, but the cascade is not turned off.
Yeah, we don't really see anything like helicity barrier or something like that. Barrier. Yeah. So this was one of the motivations, because some of these ideas are really strange.
Yeah, I think you're right there. I would suggest
Yeah, this is the future. Well, this is another point to my to-do list, clearly.
Very good. Okay.
Thank you.
More questions?
Thank you.
Okay, so Emmanuel Martin is next.
Ooh! Ah, sorry.
Yeah.
Okay. Let's disconnect.
Voilà. Okay, everybody. So I hope that I will entertain you. So I will bring you to a journey inside space-time structure of 3D all-MHD turbulence. I have a total of maybe 4 or 5 videos, so that should be fine. 20 plots and 1 slide with formulas. And I hope they distributed some 3D glasses at when you got inside, because we are going to see cool stuff. But maybe they're imaginary because I'm going to use Fourier. So let's go on. So as we well know, I will a small introduction about why do we need a multi-scale analysis for turbulence. So we know from observations, so there is this, maybe not so much, because in the last days, I only heard about structures, coherent structures, structures. Only today I heard about waves. So apparently we finally settled that dissipation or turbulence at subion scales is mostly mediated by structures. But anyway, we know that observations hints for the presence of some kind of wave-like activity in the solar wind at subion scales. And the main way that to check that, or at least that they use to check that, is to measure the magnetic helicity or some kind of proxy for the magnetic helicity, which we know that if there is wave activity by kinetic Alfvén waves, Whistler waves, or ion cyclotron waves, they should give a clear signature in the magnetic helicity in the data. And that's what apparently many people seems to find in the solar wind. But we shouldn't trust observations. And because actually many theoretical numerical works goes in the opposite direction, at least the ones that I like. And the nice thing about simulation is that they potentially allow you to see the access to the full information and to know what is going on inside your system if you are clever enough to know where to look. And like, for example, here we have just a few plots. We have like this beautiful contour plot from Luca's paper in 2015, in which we clearly see structures where we know there is dissipation. Then there is the famous work from Enrico Camporeale, in which they clearly show that the dissipation was was localized and enhanced in structures that were getting more and more localized as you get smaller and smaller scales. And then, of course, we have the PID beautiful works from Young, and then also the latest work from the group of Bill. So, and everything looks like is going into the direction of enhanced dissipation in structures with no clear presence of waves activity. Yeah, there are many works. I mean, I'm just putting random stuff that I have and so on. And then we also know that, of course, since this is localized in space, it will be a non-local in Fourier space. And so I just want to recall, since it was also recalled in the last days, one of the first work on this subject by Luca in 2017, which there is this famous plot which sketched basically what reconnection can do by non-locally transferring energy in Fourier space from directly large to smaller scales. And since I also like to advertise my work, that was a similar way of seeing that in numerical simulation of the carrying turbulence of both all-MHD and hybrid kinetic simulation in 2D, in which we clearly see that as soon the reconnection, so this one is an histogram of the reconnection rates or the reconnection events happening in the system in the simulation as the system evolves, and we could clearly see, and this is a contour plot of the nonlinear time as a function of the scale, and we could clearly see that before the first reconnection events are triggered, the dominating nonlinear time, or the smallest nonlinear time, was at the injection scale. As soon as the reconnection triggers, in both simulations we had that the smallest nonlinear time was basically going down to the smallest scale accessible, which means that energy was getting deposited there. And then as the turbulence evolved, you get to a stationary statistical system.
So, Emmanuel,
yes?
Sorry, but if the energy really is hopping over the middle of the inertial range.
No, well, the inertial range is actually here, because this is KDI equal 1, so this is the subion range.
About the diagram on the left.
Oh, this one, yeah.
If that actually happened, then if you applied the Yaglov law in the
You should see, that is true, that is true. That is.
anything. So you have to have a new term in the von Karman-Haworth equations, which as far as I know are not there. So I don't buy that picture on the left.
Well, I guess you could, yeah, okay, you could look at. This is just a sketch for illustrating the concept, but I mean, you could see that, yeah, you could see that.
I think what I would see if I compute the album early in the simulation.
Yeah, we'll go with the spectral transfer.
Current sheets reconnecting, probably that would be the
Yeah,
process.
yeah.
But then when you're quite stationary, we also have the contribution from the direct cascade and the local in Fourier space.
So it's just a sketch, it's not a...
It's just sketch. No, it's a sketch. It's a proof of concept. Yeah.
directly around the ion scales,
Yeah.
I'm not saying that the only way or the dominant channel of
Yeah.
energy transfer.
Something that may happen during the concept.
Yeah.
Yes.
So, of course, a multi-scale analysis that also look into the wave nature of turbulence needs to also be done in time, not only space. And so we need the access also to temporal frequency of our domain. And in this sense, there are many works. I mean, the one I'm citing here is one of the many, but this was done in the case of a full peak simulation. Correct me if I'm wrong. And was from Parashar, I mean, Sergio, Pil, and they were looking actually in the space-time structure of a turbulence simulation. And what was their conclusion from this is a k-omega diagram that tells you where the energy is in k-omega space in a fully developed turbulent state. And what was their conclusion is that kinetic plasma in a 2D geometry in a range of scales spanning the ion inertial scales behaves essentially as a complex nonlinear system when driven or statically or at low frequency. So mainly the take-home message was turbulence is mainly low frequency. I mean, and then we fast forward in time, we go to a work that I published last year in which I was doing the analysis that today we show in 3D, and at the time was done in 2D, and of course the referee said, yeah, but it's 2D, it's not the true system or whatever. You need a more realistic system because of course you need access to the parallel direction and the k-parallel space to have a more realistic representation of turbulence. But in this work, that's what we did. We investigated the space-time structure of turbulence at subion scale, and what we found is that we indeed found, and this is a plot from that paper, we found that in k-omega space, we clearly see the branches that were energetically excited, let's say like this, of waves in the system, but this, and so which means that waves are present in our system, but in the same work we showed that these branches were energetically irrelevant, and most of the energy, and when I say most of the energy, I say all of the energy, was at really, really low frequency. So the kinetic Alphen wave and the Whistler wave were really energetically and important with respect to the energy that was there. And so now we go to space-time turbulence in 3D plus time, so it's 4D, and this is the warm-up section of that. So how do we do it? First, we need a simulation. It's a 3D simulation. It's 512 cube with a resolution of di/8, a box size of 64 di if you do the math, which is just dividing and multiplying by 2 or something. So you have a B mean field along the x direction. Then you have freely decaying turbulence, an initial RMS of the fluctuation that is 0.24, and all the fluctuations are excited at KDI less than 0.3. This is the usual setup that we use. Then you let the simulation evolve up to the fully turbulent state is reached, and then from there you take 2 nonlinear times you take a system done on you take a temporal interval of 2 nonlinear times, and you take an high cadence interval 0.002 nonlinear times, which correspond to 0.02 inverse ion cyclotron frequencies. And so you end up with an hypercube with 512 cube times 1,100 grid points, which correspond in single precision to 4 terabytes of data. And this is just a 3D/4D representation of your of the data set that I'm going to analyze. And how do we analyze this data set? So we do it using something that I called an hybrid approach, using Fourier transform and fast iterative filtering. I will just introduce fast iterative filtering or iterative filtering to some of you. So iterative filtering is needed because in time you are not periodic, yes?
Yeah, what's wrong with Fourier?
With Fourier there is nothing wrong.
There is any difference between a Fourier transform and
Yes.
how you do this?
Yes. So I do this in time, not in space, because in time I'm not periodic. And also this iterative filtering is like the empirical mode decomposition, so it's an adaptive.
But it's only for time.
Yes, it's only for time. I'm using an hybrid. I could use it also in space, but for this approach, since I was periodic and everything was and the code is, I decided to go for an hybrid approach because to make things, let's say, to introduce a complexity level and then.
In frequency, if I know it correctly, the empirical mode decomposition is not really a proper orthogonal decomposition.
Yes, exactly. It's almost orthogonal. In fact, So what I do is that when I get a bunch of EMF or EMC in this case, and I will explain what it is, I will introduce it just.
So is there an analogy between the frequencies?
Yes.
Is the EMD and the real frequencies?
Yes. So in the EMD and also in iterative filtering, you will you can either define an average frequency of your EMF, or you can define instantaneous frequency and instantaneous amplitude. And what I did in this case, I took an average frequency base that was a weighted average of the instantaneous frequency over the instantaneous amplitude. It's written in the appendix of the paper that they published last year, if you want to. Anyway, so basically you have a signal in time, so X in this case it will be time, that is decomposed into a bunch of almost oscillatory functions, but with varying frequency and amplitude in time, plus a residual. And each function is the result of an iterative procedure in which we use a low-pass filter that is defined by this window function here to create a high-pass filter, which is basically the signal by doing the low-pass filter. And in the limit of infinite iterating procedure or application of this high-pass filter to the signal, you get your EMC. Or EMF. And then you repeat this procedure by subtracting the EMF that you obtain from the signal and repeating this procedure, so you obtain a set of time series or whatever, or EMF, in which one have like, these frequencies are distinct and amplitude is distinct in time. And then how do you get to the k omega power spectrum? So, as I said, you take this 4D hypercube, then you perform a 3D Fourier transform in space, and you obtain your Fourier field in space, but it is also a function of time. And then for each tuple, so this is discretized, so for each tuple, kxi, ky, j, kzl, with a little abuse of notation, you apply fast iterative filtering to each one of these tuple to obtain a set of EMF or EMC, intrinsic mode component, and then using this, from them, you post-process them further to obtain for each of these EMC an average frequency and an average power. And so you end up from your Fourier transform in space as a function of time, you end up with a sequence of pairs of frequency and power, and for each wave mode. And then you build a k-perp, k-parallel omega grid, and then you interpolate the power of the frequency and the power to this grid. And of course, then you sum over m, I, j, and k. By the way, the procedure, I got out, I think, about 2 billions of EMF from the whole system. So this actually is quite computational demanding in terms of, on a desktop workstation, it takes 1 day, using all the cores and all the crazy.
Does this
Yeah.
procedure have that Parseval theorem associated with it to preserve total power?
If you would respect orthogonality, yes. If you would fulfill orthogonality, yes.
Not for this decomposition.
No, not for this decomposition. If you would fulfill orthogonality, yes. But I use a further criterion that I accept, like if I have two EMF which are almost parallel, I sum them up. And my criterion for orthogonality is that if the angle between them, which means the integral mediated by in time, is bigger than 0.6, I sum them up. Of course, 0.6 is not, but that's the way we're doing it. So now you can put on your 3D glasses, and we can go to have some fun with k omega space. So here I just show a proof of concept how it works. So this is an isocontour of the k omega power spectrum of the density, and since by two different angles. Then these are the ideal linear dispersion relation surfaces of ion cyclotron, kinetic Alfvén waves, and fast Whistler waves. And as you can see, they superimpose quite nicely to this ridge and this ridge here. That means that there is indeed wave activity inside. The slow ion cyclotron branch is very low frequency, so there is some problem with that. Now, what I will show you is a movie in which I do 3 sweeping planes between the K parallel, K perp, and omega, and then the lines will simply be the intersection of the dispersion relation planes with the sweeping plane. So this is the kinetic Alfvén wave, dispersion relation, fast Whistler, slow ion cyclotron, and so on. And as you can see, there is energy around this dispersion relation. So you indeed have waves inside the simulation. But these waves are energetically important. I will try to go a bit faster. So there are waves, there is wave activity, but the energy is not contained in the wave, as I will show now. Yeah, yeah. So, I know. Yeah. So I will start by simply showing some standard, let's say some standard results. So this is your k omega, not omega, because your power spectrum when you integrate in omega. So this is a k parallel k perp power spectrum, which is the usual one that you will get with a Fourier analysis, basically. And just to show that is kind of similar to other results found for hybrid kinetic simulation, this is the power spectrum of the total magnetic field in k perp and in k parallel. And also here you see very nice similarities with the work from Luca published in 2010. So from a point of view of the spectral properties, this all 3D MHD simulation looks very similar to a full, hybrid kinetic 3D numerical simulation. And then we may ask, okay, where is the energy? So you take, this is the k perp omega plane when you integrate over k parallel. This is in k parallel omega plane when you integrate over k perp. And now you go to simply remove energy at high frequencies. And as you can see, so this will be the total power spectrum when you integrate over all omega. And this is the power spectrum when you only integrate in omega less than 3 omega I. And as you can see, most of the energy is basically at low frequencies. And you can repeat this business at 1 omega I, and it's the same. And this is perfectly consistent with what we found in 2D. So most of the power is contained in very low frequencies. Then you can expand your business further, and I will just fast forward to, but simply, so you can analyze what is the energy that is contained in the surface of the dispersion relations. And this is what is shown here. So this is the energy. This is again the energy of the total magnetic field. This is the energy that is contained in this plane, in this surface. And this is the ratio between the two, so which basically tells you that there is no, the energy of the fast Whistler branch is basically negligible with respect to the total energy. Of course, here we have a very low frequency in all cases, so we have some overlapping between the three surfaces because, I mean, you are limited in resolution. And you also, even though we may have energy there, it's still not sure that it's waves. It could be anything else. It could be a coherent structure. It could be anything. This is for ion cyclotron. This line simply tells you what is the frequency. So here 0.45 ion cyclotron frequencies. And then we go to kinetic half-and wave, which is the most suspect, the principal suspect. And again, here you see, okay, there looks like there is energy here in the kinetic half-and wave surface. So we say, okay, maybe kinetic half-and waves are energetically relevant. They are not, but I will show you now why. So one way to look at it is through the kinetic half-and wave or polarization ratios. So you take your fields, you take the power spectrum of some fields like magnetic field and density, and you do the ratio. And then if they are kinetic half-and waves, they should follow some law. And this is the result from the 2D paper in which I clearly show that the total power spectrum, the ratio of the total spectra from B parallel and the density were not made by kinetic half-and waves. And if no, everywhere. I have no time to go in detail, but I can explain you later on. Yeah, here, yes, here they may be, but not later on. And if you extend this to 3D, which means that now you have to do it on a surface, you will see that this is the theoretical plot that you should have, and this is the given by the simulation. They're very similar. If you do the ratio, you see, oh, there is a lot of, where is white, it means they are 1, so it means they are compatible with kinetic half-and waves. You see, okay, so it looks like there are kinetic half-and waves there. But we know that this is not a good proxy for kinetic half-and waves because it's also a proxy for pressure balance structure, and so it's not a good one. But if they are kinetic half-and wave, they need to fulfill all the ratios, not only this one. And if you go to another ratio, which maybe is in the next slide, maybe, yes. And you look at U perp over U parallel, and you also see that here it was never fulfilled nowhere in 2D, and neither is in 3D, because these one are very different, and it's different also here. And that was my almost last slide. I just did for fun, I tried to calculate the magnetic helicity, and this is the magnetic helicity saturated. And you can clearly see that here there is positive magnetic helicity, here there is some negative magnetic helicity, but this is just a work in progress, just to see that there is actually also the magnetic helicity as a signature. And so these are my conclusions. I think they're pretty clear. I don't need to summarize them, but we have spectrum of magnetic fluctuation is very low frequencies. There are waves, because waves are excited everywhere where there is turbulence, but these waves are energetically important. We have to be careful when we use proxies for detecting waves, because these proxies may not be the right screening, like for COVID tests. So we all know how it can work. So you can have false positive. And subaqueous turbulence looks more structure-like than wave-like. And as a side note, iterative filtering is actually, it looks a very nice candidate for analyzing this kind of data and other data. And actually, I'm also start working with other kind of data, not solar wind data, and I'm using iterative filtering, which is very nice. And if you're interested to use it, there is a Python package that is freely available here, and you may shoot me an email and I will explain you how to use it and what are the catches that they can give. Thank you.
Your last bullet here is in contradiction with the slide where you broke the data.
True.
So data are important at the end.
Yeah, no, data are indeed important. It was just, it is, yes. All MHD, 3D all MHD. 3D all MHD, turbulence, fully compressible. No, 3D all. Did you see any noise? No, because it's spectral. Yeah, it's true. I mentioned it. Oh, yeah. Yeah.
The conclusion is basically that waves are irrelevant in terms of energy content.
Yes.
But how much do you think that depends on the initialization? Because if you just inject fluctuations and you do not, if I understood correctly, you inject just magnetic fluctuations and not magnetic waves. So what do you think would happen if you inject, for example, alpha waves?
Actually, yeah, I will explain that. Actually, I inject both magnetic and velocity fluctuation, which are in equipartition, so they actually favoring alphenic turbulence.
Okay, but it's not really alpha waves.
No, there is not a 3D alpha waves.
But if you make the
I think it's okay. But just, oh.
Thank you again.
Thank you.
Presentation by Pauline Simon.
Oh, oh.
And it's a kind of
Yeah, I changed a bit the title, but it's the same. Blue. Yeah, yeah, maybe. Oh, okay. So, good afternoon. I'm Pauline Simon, PhD student of Fouad Sarawi and Sébastien Galtier. I will speak about third order law for pressure and anisotropy. My work is based on the Kolmogorov theory of exact law. And just let me do a quick reminder about this theory, even if I know that some people know it. So it allows us to have statistical formula of the rate of energy that is transferred from the force King scales to the dissipated one. And I will name this rate of energy epsilon. And thanks to Kolmogorov hypothesis, I can equalize the different rates because it separates the different range. So I can equalize by conservation. So I will just write it in after that just epsilon. And to obtain these statistical formulations, we consider a correlation function. So here is in the incompressible hydrodynamic case. So there is only the velocity for the total energy or kinetic energy. And so V is the velocity at the point R, V prime at the point R prime. And the bracket is for the ensemble average. And after some line of calculations, we obtain this exact law that gives the rate of energy in function of the scales, so the increment of positions, and structure functions. Such kind of terms I will call them after that flux terms because it's a flux and the divergence of a flux. Yeah.
Is it the cascade or dissipation rate? Is it the dissipation rate per unit mass or per unit volume?
Is the
overall?
It's incompressible, so the rho 0 is constant, and
But the units then?
actually it's a density of energy. So
That's an epsilon.
yeah.
Not epsilon mass is unit mass.
Yeah.
So epsilon is unit to 4.
Well.
Okay.
Yeah, it's the density. Okay. So this theory has been extended to incompressible MHD and all MHD, and also to compressible models. And in the case of compressible models, you will obtain the flux terms different than the previous one, and also the source terms. So this is the source. The S prime is the conjugate of S, and so it's another form of, yeah, it's like a container. Bon. Then this is about one of the questions is, are these extensions able to reflect kinetic effects? And for instance, Ferrand and al. 2021 show that the incompressible Hall MHD can capture the Landau damping, the amount of energy that is dissipated by Landau damping. So here. And about for my PhD, the question is, what about pressure anisotropies and instabilities? As you can see in Osman and al. And Hadid and al., the along the threshold of instability of pressure anisotropies, you will obtain bigger cascade rate. And in the case of Osman, it's with incompressible cascade rate. And in the case of Hadid, it's compressible cascade rate. So we have a difference. Yeah.
The y-axis is in the same units?
The y-axis, yep, it's in the unit of epsilon. Yeah, for everything, for every epsilon, I think.
And what was done here? Is it the same units as the one which is on the...
This... no, because I don't think so, because here it's in observations, so you have units. Here is in simulations, normalized simulations. So, the spatial scales are normalized with the inertial ion inertial range, and I think the velocity is normalized by maybe the Alven velocity, but I have to verify. So, yeah, why?
What has been done in this paper?
They show that here is the incompressible Hall MHD results. Is the cascade for the incompressible Hall MHD. And the difference between this curve and this curve, that is fulfilled by this, it's a correction obtained via a computation of the Landau damping rate, amount of energy that is dissipated with Landau damping.
So there is some turbulence
yeah.
in somehow another way, and then there is some Landau damping on top of this, or?
I think it's a way to just extend the cascade to subionic, and after that scales, and taking some kind a part of the dissipation. In fact, but it's not my work, so maybe I can speak about my work. Okay, so my work is, can we derive an exact law that will explicitly take in account these kinetic effects, but not Landau damping, the pressure anisotropic potentially kinetic effects. Ouais. So I consider magnetized compressive pressure anisotropic fluid. So with the velocity, the Alven velocity, density, tensor of pressure, and internal energy. About the correlation function I choose, it was this. So it's just an average of these terms and its conjugates. And on this term, you will see you can recognize the kinetic contribution, magnetic contribution, and internal contribution in the total energy, which is an invariant in the system. So about the model, I considered the density equations, the velocity equations, and the internal energy conservation equations. So here for the when it's a tensorial pressure, and the assumption I took is that the heat flux is constant. So you don't have the divergence of the heat flux here.
So no heat flux, right?
No heat flux, yeah. I can zero heat flux in the inertial range I consider. Because the exact law I obtain is valid in the inertial range.
For both ions and electrons, right? Okay.
But in the dissipative one, it's quite different. Then I obtain what I called a general exact law for a tensorial pressure. General because if I take a form of the pressure of tensor pressure, closure equations, for instance, polytrope, isothermal, thing, and if I with this closure equation, I compute an internal energy explicit form, I can obtain all previous exact law with the same correlator. But from this general exact law for tensorial pressure, I obtain also gyrotropic laws. For instance, for compressible CGL, so sugar and low biadiabatic model. And also a correction of the incompressible law of Politano and Pouquet, this one. A correction depending on pressure and isotropy.
Sorry. So you want to study kinetic effects, right?
Yes.
Heat flux equal to 0 for particles?
Yeah, no, it's not, okay. Maybe was a bit optimistic with kinetic effects. Not kinetic, it's just, it's instabilities. So you can compute instabilities in MHD model if fluid models. So yeah, it's a fluid-like kinetic effect. Like Landau damping in Landau fluid.
It's a typical closure, this of the two-Goldberg law, when you want to include kinetic effects in a just MHD, like, because this anisotropy develops also scales larger than the Ionsky depth, but you don't need any Ionsky depth. That's it. It's a closed system.
Okay.
Thank you. Then this is the law in the case of CGL. I show you here the case where I developed the pressure tensor because you can see this type of term which depends on 1 minus AP. AP is the anisotropy rate, the pressure, the perpendicular pressure on the parallel one. So these are the new terms, really new terms, depending on the anisotropy. And when you take the incompressible limit, this one and this one will be cancelled. And only this one will stay. And it's conjugate, of course. So this is the incompressible limit. You obtain the Politano and Pouquet law, and also V correction depending on 1 minus AP. This correction is a source term, so it can be hard to compute in observation if it's a monospacecraft because it depends on a local divergence. But in the theory, it works, and depending on the sign of these terms, the pressure anisotropy can diminish or reinforce the cascade, so add more, so epsilon. So, I have time or not for this?
You have 7 minutes
Okay.
until the end.
Until the end. There is questions about the overworks because this is just one. It's just curves that I obtained last week, and it's just preliminary results. So if you have questions about the last part, we can take time about the last part. No questions?
Questions? You have more material, though.
Yeah, but do you have questions for what has been presented?
Well,
I have some numerical.
I think there's a problem with the heat flux term because you kept the brackets, right? I mean, so
Yeah.
you're averaging over a homogeneous medium,
Yeah.
or you're averaging over a periodic box, so the divergence term goes away, unless there's a heat flux at infinity or something like that.
I don't know what happened to the X-flux. I didn't make the computation, the calcul.
I don't think that's a problem. But it seems to me that adding the pressure-strain interaction in is like keeping the D term in the Hellinger
Yeah.
in the von Karman-Hallworth
Yeah.
equation. So yeah, that should help make things add up better, I would think. That's the dissipation term.
Yes. So I take in part of the dissipation if there is FLR terms, for instance.
I have a general comment. All these compressible Yaglon papers by Banerjee and Claire, and this is a continuation, they study the cascade rate of the total energy, including the internal energy.
Yeah, so because it's the invariant.
Yeah. So, and they, so, okay, you can do whatever you want. Your results, your cascade rate includes the cascade rate of the internal energy, whatever it means, if it exists. But it also means if you estimate some kind of cascade rates from observations or from simulation.
We have a flux of internal energy.
You calculate energy, internal energy redistribution rate. And it's not really important if you want to study the heating of the solar.
We have a flux of internal energy.
That's the point. My question is that you are injecting energy because epsilon is the dissipation rate, right?
Yeah.
So you are injecting energy.
Yeah.
So the full energy, the total energy of
Yes.
the system is not conserved.
In the inertial range is conserved. So, yeah. I consider that in the inertial range is conserved. If I didn't make a...
Can you really call it a dissipation range if you're including the dissipation function in that range?
There is an issue that, there is no guarantee that the way how we include the internal energy is compatible with the kinetic energy and magnetic energy.
But there is exchange between the three...
that doesn't really, it's not really compatible with the description of the kinetic energy and magnetic energy. For that, you have a quadratic formula.
we prefer to not take away this part because it exists and it's in the invariant. So yeah.
What is invariant? I am lost.
The total energy.
Total energy. So what is your argument? I don't understand. So
if you measure the cascade rate of the total And the internal energy.
internal, yes.
So this gives you the cascade
It
rate.
is heating internal. What do you
Yeah,
think?
it's somehow, in principle, there should not be any dissipation.
It should be dissipation, but
It's an invariant.
Yeah, but there is some reversibility in the internal energy, so you can have really exchange. Is not the energy that are going to internal energy is directly dissipation. It's the it's
to say that your epsilon injection should be equal epsilon magnetic plus kinetic equal epsilon internal.
But better
Mm,
because
not-
before, even he was speaking about compressible OLMHD, except he was using a variable which was hiding a triple correlation. Here is explicit. In his case, he was using an exastal variable with a square root, which makes you really not quadratic calculation. No, it's very similar. It's quadratic if you use the fake exastal variable, right?
Something more similar because Transascendent variables are present only for the
But it's a trick. So,
It was
it's
not
not a
on
trick.
the side.
But it doesn't matter. Okay, you can use delta rho u, delta u,
Okay.
or delta
No, it's fundamental, that trick, to have the law that's such a beautiful compact tool. Right?
It's not that beautiful. It's not that complex.
What I know for you, but it's beautiful.
Thank
Okay.
It's interesting.
Okay,
I think it's a
Okay.
I fully agree. They are kind of, although we know how is the workshop, there are still a few rules.
Yeah.
Otherwise, we will stay here until all night.
Yeah.
Do you want to show maybe one or two?
My
No more?
okay.
It's finished. Okay.
No, yeah, but there is the conclusion with my two articles and the numerical results. So this is my first numerical result I obtained last week. So it needs refinement. So yeah. What is this? I separate the contribution of okay, the isotropic pressure and other terms that do not depend on the pressure. So in the flux, the source, and all case because I used the simulations used by Renaud, Ferrand, and all in the previous paper. And it's CGL all MHD simulations. So I have the all, and I have to take all corrections. And I separate them from this isotropic all cascade rate for isotropic all model. I separate donc the gyrotropic contribution, which one we find in the flux, and the part we find in the sources. What I want to show here is that the isotropic one results is in blue here, and here it's under the orange one, and the gyrotropic one is in purple. So we have a difference between the gyrotropic and the isotropic. So the gyrotropic contribution is interesting, and it's interesting in this part of the scales, perpendicular scales, because it's the whole part and the subionic part, but we have also a contribution in the MHD part. So yeah, and about the dominating term, you have the flux, isotropic flux, the whole term in the subionic range, and also here the source, the gyrotropic source. And in this gyrotropic source, one of the biggest source is the one which stay at when we take the internal the incompressible limit. So yeah, but it needs refinement. And yeah. Do you have questions about this? Thanks. Thank you.
One more question, maybe? There are some.
Okay.
Okay, I think you
Okay.
can discuss with people.
Yeah. So, but the theoretical work was published in two papers, one for isotropic pressure and this one for tensoral pressure. So yeah.
Thank you again. So last talk for today. Steve will replace Soham Roy.
I was going to take a picture of your last slide.
Okay.
Maybe you can email me.
Yeah, I can email
Good job.
Do you want this or?
How does it work?
You put it on your ear.
Oh, okay. How, like this? Hello? Is that working?
Looks like.
Okay. So I'm going to pretend that I'm Soham Roy right now, who's my graduate student. Probably if you meet him, you can tell the difference between him and me, I think. Good? Where's the stick? Is this working? I'll try to make this quick because people are tired. So a usual cast of characters, including people from the MMS project. We're going to talk about electron-proton heating. Okay? Good. Okay? Okay. Oh, well, you know, yeah. Pressure strain, flow into thermal, J dot E, flow into in and out of magnetic energy, electromagnetic energy. Decomposition of pressure strain, everybody knows it at this point, right? This is the way you go through the talk quickly, right? Okay, conservation of energy in a pretty good PIC code. If just to say it simply, this is the change of thermal energy in the PIC code. If you take J dot E, remember in MMS community, J dot E is called the dissipation. They don't even bother to qualify it. They just call it the dissipation. Well, here's the dissipation integrated over time, and it doesn't come close to accounting for the thermal energy increase. So I guess it's not really the dissipation, but we knew that from the previous slide. On the other hand, if you take the pressure-strain interaction and integrate it, it's not so bad, right? It accounts for the internal energy increase pretty well. Yes? Sorry? The electron beta, and that's, I'll look it up later for you. It's an old, there's a reference. That's from Parashar et al. 2018. I'll never get through the talk in the time I want to do it if I have to look up electron betas. But it's probably about 0.6. I don't think there was any reason to make it different than the proton beta. So, one thing you can do is you can look at Politano-Pouquet. Remember, this is a compressible plasma, right? And has Hall effect and everything else. But the cascade in the inertial range is mostly dominated by the incompressible stuff if it's a nearly incompressible simulation, which this is. So you can, we're using 1100 burst mode MMS data sets. So we're not controlling for any parameters. We're assuming that if there's 1100 of them, it's probably a pretty good ensemble, we think, in the magnetosheath, yeah. So you can compute the von Karman decay rates at the outer scale, and you can compute Politano-Pouquet. and at the inertial scales, and you'd expect them to be about equal. And if you plot them, these are binned now. There's 1,100 samples over different von Karman rates, and at least over a pretty wide range of cascade rates. It looks like it's a quasi-steady cascade. I mean, you can argue that there's some saturation here, and in the paper we explain some reasons for these possible departures at very high and very low cascade rates. But we want to look at other stuff here. Okay, so another thing you can do here is to look at the pressure strain and also the total pressure strain and the pi d. And you can bin those according to the average of the von Karman and Politano rates, just averaging to get rid of a little noise. And you see that it breaks up into two different groups. One is the full pressure strain up here, which they're sort of scaling linearly with this, but not at the equal line. And the other one is the incompressive, or gyroviscous, if you like, pi d, which is much closer to lying on this line. And this is something we deal with all the time with magnetosheath analysis, especially when we compare to simulations, because most of the simulations that we do, the compressive heating is almost negligible compared to the gyroviscous kind of pi d. But in the magnetosheath, it's the opposite. The magnetosheath is very, very compressive. And we don't really know exactly why that is. We think it might have to do with the solar wind slamming into the plasma and squishing it together, and it gets heated. And then when it flows around the Earth, we think it probably cools again. But that's kind of like saying the solar wind is expanding, and expansion is important, right? There's people here who believe expansion is important, but it's also locally heating. So the fact that it's expanding and cooling doesn't mean that it's not locally heating. So we think it's something like that, but it's not completely understood yet. So we're really going to concentrate more on these blue points. Okay, so the transfer rates agree with the incompressible theories. So now, if you look at the total heating rate, now this is not computed from the pressure strain interactions for the ions and the electrons, and add them together, right? We tried to already convince you that they're kind of comparable to the von Karman rates, but now we can bin the ratio of ion to electron heating in bins of total dissipation. And now the MMS data is up here, and we also added a whole bunch of simulations from 3D PIC. There's only one of them here, and a solar wind, a canonical solar wind point, and a bunch of 2.5D simulations from Tulsi Parashar. And now you see that they spread out like this into two groups. Now, why plot this at all? Well, we know from Kolmogorov that if Kolmogorov applied to MHD, that the increment should scale like epsilon to the 1/3. So therefore, you would think that at increment equals di, it would marginally scale it's still the inertial range, scale like epsilon to the 1/3. So therefore, the hypothesis that we wrote in the 2016 paper is that QI over QE should other things being equal, should.
Why just looking at the data and concentrating on the MMS data?
Okay.
But there is at least 2 order magnitude there on epsilon on the x-axis, and really it doesn't match at all QI over QE. Why the data do not match with the epsilon to 1/3 there? I mean, suppose you look just at the data, you do a fit there. Okay?
Well,
I'm doing a fit now.
It's horizontal.
No, well,
it's the other way actually. What's wrong?
don't do the fit.
Okay.
Okay. I mean, the thing is, there are a lot of uncontrolled parameters here, right? And I think we're going to get into one of them in a minute. But that's why we wanted to include this to see overall. I mean, think of the MMS points as being 1 point, and think of these as being 1 point. They lie on the epsilon to the 1/3 trend line, right? there's a lot of orders of magnitude of uncontrolled parameters here. Now, the interesting thing is all of these points are near beta equals 1, and all of these points are near beta equals 10. That might have something to do with what's going on. But the idea here is basically that the stronger the increment is at the ion scale, the more likely you are to heat the protons. And that's something that Dimitrik and I said in the early 2000s, and then Chandran built the so-called stochastic heating, built on that idea. And then Tulsi and I had done this, and we published something in 2016 that fit a bunch of simulations pretty well. And here we're introducing some observational data. So let's move on, because we know that the betas are very different in these two groups of points. The other thing that we said in this paper was that the ratio, all other things being equal, the ratio should also scale like the cyclotron time over the nonlinear time evaluated at di. That was another postulate in that paper, which seemed to work for the simulations. Well, how about if we look at it for this MMS and simulation points here?
Why so?
What's that?
Why this ratio and not, for example, divided by cyclotron resonance of electrons?
Well, because you have a cascade, and the cascade comes down to ion scales, and then the ions see two things. They see the gyro motion, and they see the randomization due to the nonlinear time. Okay. And if the cyclotron time is very short, then their orbits won't be perturbed, and the cascade just goes right through them and heats the electrons. And this was also motivated in part by a whole bunch of observational stuff that the New Hampshire group did, where they looked at the slopes in the kinetic range as a function of the cascade rate. So it looks like you really have to have a stronger cascade rate to heat the ions, but then the slope gets steeper in the kinetic range. So this was a distillation of that. It was a hypothesis. But if you look at these data sets, you see that, interestingly, the set of simulations that we had before, except for this one, really lie along one trend line, and the 1100 MMS observations also lie along a parallel trend line, but it's parallel. So what's going on? Okay, so our referee, when we submitted this, who I think is at this meeting, but not in this room right now, made the very intelligent suggestion that we should look into beta a little bit more carefully, because these are all beta equals 10, and these are about 10. I mean, actually, there's a wide variety. And the other ones are all scattered around beta equals 1. So we sort of went back to the drawing board a little bit, and we looked at everything and looked at the ratio just with respect to beta, holding the other things constant, and or holding them, not taking them into account. And now you see that there's a nice trend line with beta, and a fit to that gives beta to the 0.82. So to
understand it better a little bit, because what's the physical meaning of having that beta dependence? There is a process like, I don't know, lambda damping in, or there is any...
Oh, well, part of it is that when we constructed this argument about TCI over tau nonlinear, we could have put in the gyro radius. And the difference between TCI over tau nonlinear at the gyro radius and at the DI is some power of beta. Yeah, but in addition, if you go back and look at the Matthews et al. 2016, we said we don't know what the beta dependence is of this whole process. So it actually had an arbitrary, if you look at that paper, it has an arbitrary function of beta multiplied by TCI over tau nonlinear. Now this is, in effect, an empirical determination of that arbitrary function. So this is empirical, this is like still physical reasoning for this one. So there's a formula for QI over QE, and there's a paper on this. And if you now, once you have assembled that semi-empirical formula, you can go back and look at our original set of data, and that's how well that formula accounts for these 1100 MMS intervals and the simulations. The interesting thing is when we started, the simulations agreed better than the MMS data. Now the MMS data are agreeing better than the simulations. So the real answer is probably a little more complicated than this.
You're biased.
Huh?
You're biased by
Biased by the data. I mean, well, my thesis advisor, David Montgomery, used to say, the problem with space physics is there's too much darn data. So anyway, I tend to lean towards the data, I guess. But anyway, this isn't bad, we think, and that's kind of the conclusion. But it's sort of semi-empirical. What do we have here? Pressure strain agrees well with increase in thermal energy. J.E doesn't. The energy ejection rate at large scales is almost equal to the cascaded energy in the inertial range. The NMHD scale energy transfer and the total dissipation are roughly the same. QI over QE increases with total dissipation rate for sure, kind of like epsilon to the 1/3. It also increases with TC, cyclotron over tau nonlinear. If you put it together semi-empirically, you get this formula, which we think is not too bad. Well, how good is it compared to some other theories? That's the question. There are other theories, as a matter of fact. There's theories by Elliott Quattart, Howes, Kawazura, and anyway, here's us here, and this is Quattart 98, Howes 2010. We think that our semi-empirical theoretical explanation is pretty much overall as good as or better than the other ones. So I don't know, it's a matter of opinion. The thing is, in these other theories, you need to say what the ratio of the temperatures is, and we don't say anything about that. It's changing. They're all over the place. Yes, sir?
Is the label on the x-axis correct? Because that's not your expression, that's just beta.
Oh, I'm sorry, you're correct about that. Here, the purpose here is to see whether our semi-empirical determination, you're right, good catch. This is really a test not of the whole theory, but of whether our beta to the 0.8 part of it is correct or not, because that might be questioned. And I mean, these are theories for the ratio as a function of beta. Yeah. We didn't go, I don't know how to plot these other theories on the other plot because they're not looking at those parameters, right?
But the data nicely avoid all the kind of theories there, right?
What's that?
The data, they're avoiding a little bit, a lot of that.
Yeah.
All of them.
Well, that's right. So no, that's a really good. No, that's a good point. So when you see how not well what am I? Yeah. So when you see this kind of deviation from the theory here, I actually think that relative to the state of the knowledge of this, it's not so bad, right? I mean, room for improvement. But it is a couple of orders of magnitude, and if you're willing to accept factors of 3, the trend is correct. But I don't think there is a well-accepted theory for QI over QE. One of the things we want to do is to build this, or maybe some improvement of it, into the macroscopic MHD codes to fluid. Because there you have beta, you have TC, I, and tau nonlinear, and you may, instead of saying QI over QE is 0.6.
But then you have to close your system to the heat flux with the MHD. No? You need to add an equation for the energy, right?
Well, in the Usmanov code, there's electron heat flux. It's too fluid, and electron heat flux is in there. The ion heat flux is neglected, which most people do. But you have to know how much of the turbulence energy is deposited into electrons and how much is deposited into protons. And every one of the major solar wind global codes that I know of just says that ratio is some number. And it's usually like 0.6, something like this. But it varies, right?
We have a number of observations of TE over TI at collisionless shocks in supernova remnants.
Okay.
And there it looks like that TE is constant, independent of shock speed, and TI, of course, varies with shock speed, so you get very low electron heating.
Mm-hmm. Very little electron.
Very, very little electron heating.
Do you know what this number is for?
I don't know what that number is. The plasma beta is behind the shock is very, very high, of course. And we think that what's going on there, the electrons are heated in a precursor established by cosmic rays, and the ions are heated behind the shock, and it's two different mechanisms.
Yeah, so if you're looking at different regions and different mechanisms, then that's a more compound problem than this.
That's how we can make sense of it. But I mean, again, it's a question of hand waving and trying to
Yeah.
make sense of it.
Well, I've done plenty of that here too. So.
Here, two different things can be solar wind and magnetosheaths, right?
Yeah.
They seem to follow the same story, right?
Well, that's part of the point. We have 2D simulations, 3D, solar wind, and 1100 magnetosheath intervals. And this is 1100 magnetosheath intervals. So, I mean, that we don't have 1100 simulations. Each dot is one simulation, right? And the distribution of parameters in those 1100 is really, a lot. The compressibilities, the Mach numbers, everything. And yet, it's encouraging, I think, that they follow that line. So, it's not proved, but...
Have you tried different things to compare with different things on the x-axis? Have you tried?
Well, I showed you some. I showed you just the TCA over TI, and we did the pieces. There's other things we could try, right? More complex dependence on the beta. Yeah, there's a whole world of things that could be tried. I'm finished talking. I'm finished.
Okay, good.
If everybody, what's that?
Any more questions or extra?
Yeah. I deserve being harassed much more than that. But yes, sir. You want to? I can't sing. I can't sing.
So if I would enough to look at, I have two questions and one comment. One question and comment and a comment. So if I wouldn't say, if I would appreciate this plot, I would say that, as some other people noted, that the simulation doesn't look like occupied by follow MMS, but if I then look at solar wind and 3D peak, I would slightly think, okay, maybe solar wind agrees with, let's say, the trend in simulations, but magnetosheath is another story, because the trend is different. And my second question, which is just, so these are 3D and 2.5D peak explicit peak simulations. So could it that be that the fact that you are considering relativistic effects because your omega p or omega c must be very low?
Yeah. Also mass ratio.
Yes, also mass ratio could have been that the curve will change if you go to more realistic conditions for.
Yeah, maybe if you change the mass ratio, they rotate. I mean, there's a lot more to do. The subject is far from finished. Thanks, everybody. I think they let me off easy.
Okay, so are we done? We are done. So see you tomorrow morning.
What time we start tomorrow morning?
Tomorrow we start at on the program.
Nothing changed?
9.
Nothing changed? It's still 9?
Yeah.
Maybe 9:30?
You want to start at 9:20?
9:20? Is it okay? I don't know. Everybody's here then tomorrow?
Everybody will be here, yes.
Everybody will be here in the program. So what time we start? As it's planned? Yeah. Yeah, because people are already leaving here.
Bill, is it fine if tomorrow we start at 9:20? Is it fine if tomorrow we start at 9:20? You have it.
Thank you very much.
When are you going to talk? At 9:30?
She's the first. She's the first tomorrow. 9:20, 9:30. Yeah.